This conference will now be recorded.
Hello everyone. A very good morning, good afternoon, and good evening to one and all present here for today's virtual conference. Before proceeding further, let me introduce myself. I am Rees. Pleased to welcome you to this conference. Firstly, I would like to thank the researchers from the respective fields of research for taking their precious time out and making this to this event. It will be my pleasure to introduce you all to the speakers who are here today to share their knowledge. Before we begin with today's session, please allow me to deliver a brief introduction about our organization and further instructions to proceed. Scisynopsis conferences provides the opportunity to discuss latest cutting edge clinical and basic scientific research from the elements and fields of life sciences, medical, clinical chemistry, technology, medicine, pharma, management, engineering, and technology. Gain the expert opinions on current research and issues across the breadth of science and engineering. We remain curious and passionate towards providing a forum of scientists, researchers from university, research institutions, companies, laboratory with the latest knowledge and topics with a wide range of great events to gather knowledge that can reshape the today's world. Thank you once again to all our attendees of today's conference and hope you will gain knowledge from the sessions today. Now, as some of our attendees are new to GoToMeetings app, so I will explain you the important settings and procedure how to begin with that. As you have joined through the link provided, you can see the screen where you can find four icons at the bottom center of the screen. The first one is the mic button. Click on that to mute or unmute yourself so that I request you all to stay muted while our speakers are presenting their research work so it does not cause any disturbance to them. Camera button, you can use this button to share or unshare the web camera. If you have the option to share the web camera, you can use it or it is completely your choice. The screen button, you can use this button to share or unshare your screen. During your During your schedule, when I call your name from my side, I will be making you as a presenter. When I will give you the access to share your screen, then you can need to click on the bottom and you will find a pop-up window which you should accept to share the screen and you can proceed further. For the MacBook or Apple device users, once I make the presenters, then you will need to give permission to share the screen in your system preferences. After that, you need to log out from the session and need to join again from the same link and share the screen for the presentation. The last one is the leave button. This is your last icon. clicking on this button, you will leave from the session. On the top right corner, you have three icons: people, which shows you all the attendees of this webinar; chat, in this option, you can chat with me or any other participants, and you can ask with me any queries. The settings, you can use this button to check for the settings for your speaker and microphone. So as I mentioned, kindly remain muted during the presentation so that the presenters don't get disturbed, and for any questions you can ask me or can write in the message box too. Finally, I would like to request you all to give a brief introduction about yourself before starting with the
Anche
session
attacking
so that
I got successfully.
we can know about you virtually. Now let's move into our session. The first presenter is Dr. V. Anil Kumar Vikram from Vikram Sarabhai Space Center, Indian Space Research Organization, India. Hello, Dr. Anil Kumar. Are you ready with your presentation?
Yeah, hi. You are able to hear me?
Yeah, you're audible. Now I'm making you as a presenter. Kindly click on the screen
Yeah,
button to share your screen, please.
sure. So, are you able to see my screen?
Yeah, your screen is visible. Make it as a presentation mode and start your presentation. Okay,
Yeah,
perfect. You can start.
yeah. Okay. So, good morning or good afternoon, wherever you are. This is Anil Kumar from Vikram Sarabhai Space Center, Indian Space Research Organization from Trivandrum. So, I'll be presenting on metal additive manufacturing for Indian space program. Okay, so just to give a glimpse of our organization, we are a Government of India organization, and we are responsible for research in space activities for our national requirements. So the vision of our organization is to harness, sustain, augment space technology for national development while pursuing space science research and planetary exploration. So with this vision, we have formed our mission statements such as development of launch vehicles, satellites, navigation technologies, remote sensing program, space-based navigation, space-based applications for societal development, research and development in space science, and planetary exploration. So towards this, we have important activities which all of us are responsible. So as a part of that, I am responsible for realizing the materials required for both launch vehicle and satellite programs of ISRO. So mainly, I deal with the titanium and superalloys and also additive manufactured components. So this would be the outline of my talk. So I would be just giving an introduction about the metal additive manufacturing process and the processes that are suitable specifically for space applications. And I would be covering a few case studies in metal additive manufacturing, what we have done at Vikram Sarabhai Space Center, mainly focusing on the space applications. And of course, I'll be talking about the opportunities and conclusions in this metal additive manufacturing area. So as you all know, space industry is characterized mainly by complex products, but in low volumes. So additive manufacturing is especially for space applications. It forms a value proposition mainly because of the challenges involved in realizing components for space applications. So the main challenge in implementing additive manufacturing into mainstream is quality and consistency. So we need to have or produce all our products with consistent quality and also repeatable quality. So that's why we call them as consistency and quality. We are also looking at optimizing product design for increased functionality by additive manufacturing, such as internal cooling channel applications. And we are looking at more near net shaped components and weight optimized products that can be produced by additive manufacturing. And we are also looking at possibility to make late changes in the design iterations by additive manufacturing, because in space systems we need to adapt to different changes that are demanded by the end user. So there may be some late changes in design, and for that different iterations would be required. And when we adopt additive manufacturing, we have that flexibility to go for different iterations very late in the design cycle. Also, additive manufacturing has the potential to substantially decrease the lead time and move to in-house manufacturing. And when we talk about today's world, there's a lot of competition around. So earlier, when we talk about space applications, we were looking at weight and performance. Whereas when we're talking about present day space applications, with the emergence of new players in the market like SpaceX, the focus has been towards cutting down the cost. So to achieve competitiveness, we need to cut down the cost. So additive manufacturing is one area wherein we can cut down the cost of launch vehicle and satellite systems. So coming to the capabilities of additive manufacturing, we can make parts or structures that are normally impossible or difficult to manufacture conventionally, and we can also make parts with integrate internal structures or complex shapes. A single additive manufactured part can replace an entire multi-part assembly as shown here. We can have multi-part assembly that can be printed as a 3D printed as a single component, and we can manufacture parts on demand without the need for an entire factory. So conventionally, we need to have an entire factory kind of setup to make a particular part. So when we have so many parts to be made, we need so many production lines. So that is not there in additive manufacturing. You can make any new part without the need for an entire factory. And we are also looking at production of novel materials with unique mechanical and physical properties. And we can also add new functionality onto existing part, or in fact, we can even repair the components by using additive manufacturing. So here are few examples wherein you can adopt topology optimization. You can make conformal cooling channels by additive manufacturing. We can also look at weight reduction and performance gains by going for additive manufacturing. And as I already mentioned, we can integrate a multi-part assembly and print it as a single component to optimize the design. So coming to the motivation for employing additive manufacturing for space applications, you all may appreciate the cost of injecting a payload into space can vary anywhere between $5,000 to $20,000 per kilogram. So effectively, an optimized design which can lead to weight savings or part count reduction would directly result in substantial cost savings of this order. We can also look at cost-effective, lighter and reliable systems in a quick turnaround time. We can look at advanced alloys with exotic physical and mechanical properties. In space applications, we have almost always combination of alloys such as bimetallic joints or multi-material components or functionally graded materials. All these can be made through additive manufacturing route. And of course, for academicians and scientists like us, there's tremendous scope for research and development. There's tremendous challenge for metallurgists to develop new materials for hostile environments, especially when we are talking about space applications. We are looking at extreme temperatures such as cryogenic temperature, ambient temperature, and elevated temperature. We are looking at environments that are oxidation prone or corrosion prone, or embrittlement of materials can happen. We are looking at environments with static and dynamic loads, pressure conditions, and of course, being space applications, we are looking at minimal design margins. So with this motivation, we look at what are the different metal additive manufacturing processes that are available for realizing components for space applications. So we can mainly classify the metal additive manufacturing process into these broad areas, such as the powder bed fusion. We can use either an electron beam as a heating source or laser as a heating source for melting and depositing the material. And we have another technique called as directed energy deposition, where you can use powder or wire as the feedstock for deposition, and you can use either a laser or an electron beam or plasma as the heating source for melting and depositing. Of course, one process that has been gaining more popularity in recent times is cold spraying. There are other variants of metal additive manufacturing process which I am not covering today, but I'll touch upon in one or two of my slides. So when we talk about metal additive manufacturing process selection for aerospace applications, we look at all these attributes. So we look at mainly the alloy selection, the overall part size, complexity, the feature resolution to be the component to be printed, the feedstock that is required, the parameters that is to be used to make the component, whether the component is a single or a multi alloy component, and what are the process economics, whether the processor is available, whether it is industrially mature, and what are the post-processing aspects, the metallurgical characteristics, and the properties. So among all these, I have highlighted here three main attributes, that is the overall part size of the component, the feature resolution, and industrial maturity. So any process that is having a TRL level 6, that is technology readiness level of 6 and above, we can choose that for aerospace application. So we know there are different additive manufacturing processes that are available worldwide, and this particular graph, it shows the relation between the build height and the build diameter of the component that can be made through different processes, and this is ever changing, I should say. So the present laser powder bed fusion capability is limited to 1000 mm by 1000 mm by 1000 mm volume. Whereas when you talk about other additive manufacturing process such as wire DED process or even a cold spray kind of process or electron beam wire DED process, we are looking at components of the size of around 4-meter class. So these are the different processes that are available and their size capability. So we'll keep this in mind when we think about adopting different processes for making the components for space applications. So this slide again, it gives a relation between the feature resolution and deposition rate of various metal additive manufacturing processes. So as you move towards the right, from the left to right, we can see that the feature resolution is increasing, whereas the build deposition rate is decreasing. So effectively, the powder bed fusion process, they are capable of making components with very high feature resolution, but the deposition rates are very slow, and also the component size of the components are lower. So when we move towards the left, we see here that the deposition rates are quite high, but the feature resolution is reducing. So when we talk about additive friction stir deposition or cold spray or electron beam with wire DED process or additive uh, with wire DED process or laser with wire DED process, we can see that the feature resolution is reducing. And one important point to note here is as we move from right to left, we can see that the feedstock size is increasing with an exception of cold spray process, which uses again powders which are very fine in nature. As shown here, they use powders of around 10 to 45 micron. Again, the powder bed fusion process, they use powders ranging from 10 to 45 microns in case of laser powder bed fusion. And in case of electron beam powder bed fusion, they use powders which are ranging from 45 to 105 microns. Whereas when you talk about most of the DED process, we are looking at wire of the sizes of around zero point 0.6 to 3.2 mm diameter. And when we talk about another important process such as friction stir additive manufacturing, we can use a feed shock in the form of rods ranging up to 10 mm diameter. So this slide gives a glimpse of metal additive manufacturing for space applications. It gives a world scenario. So there have been many success stories. So this slide just gives a glimpse of such success stories across various spacefaring nations which have developed components for these applications. So we at ISRO had developed our own Northwest Fleet Cluster Assembly, which has been flown in GSAT-19 way back in 2017. And we have seen the Super Draco engine and Merlin engine main oxidizer valve have been made by SpaceX through additive manufacturing route. ESA has developed the propulsion module for Ariane 6, which hitherto used to be made by brazing all these elements individually onto a plate and realizing through a more cumbersome fabrication, conventional fabrication route, whereas now they are making the same through additive manufacturing route. And we have also seen Lockheed Martin develop propellant tanks for space applications for titanium applications as shown here. And we have seen Relativity Space develop the propellant tanks as well as the entire rocket through additive manufacturing route. We have also seen our own startups such as Skyroot and Agnikul. They have 3D printed their cryogenic and semi-cryogenic engines. And we have from Rocket Lab, the Rutherford engine has been made through additive manufacturing route. And Fraunhofer IWS, they have developed the aerospike nozzle through additive manufacturing route. And of course, Cellcore again has developed the engine chamber through additive manufacturing route. So these are a few success stories across the different space agencies across the world who have adopted additive manufacturing into their supply chain. So now I'll be moving on to a few case studies in metal additive manufacturing, which we have adopted at Vikram Sarabhai Space Center. So here you can see two components that are made through laser powder bed fusion process in SS316L, and these particular components we have made through a 3D printing route, and we have done extensive qualification of these components before inducting them into flight. We have also carried out structural testing to 4 times the expected loads. As shown here, the structural testing is being done by use of actuators by loading the components to 4 times the maximum expected loads. And we have done extensive NDT characterization through both computed tomography as well as X-ray radiography to see the presence of any defects. And we have done mechanical property characterization, and you can see here Earlier we used to realize these brackets through forging route, wherein the properties are much lower, and when we make the same thing to 3D printing route, we have found that the properties are much higher. Of course, with certain compromise in the elongation, which is not a problem because our design elongation is less than 30%. And after carrying out all this qualification, right from the powder, the material, and the parameters, we have carried out detailed qualification as per AWSD 20.1. And once these components were qualified, we have flown this successfully in our D1 and D2 flights of our small satellite launch vehicles. So yeah, this slide again, it gives a comparison. When we realize this bracket through forging route, we used to make a forged block of around weighing around 100 kilograms. So you can see the amount of material wastage here because the final component weighs only 3.6 kilograms, and the minimum yield strength used to be around 250 MPa. And the cycle time here to be noted is when we make the same thing through additive manufacturing route, we could cut down the cycle time from 55 days to less than 7 days. Of course, the cost wise, there's no real advantage, I should say. In fact, there's a deficit here. But when we try to adopt a design for additive manufacturing for the same bracket, we could cut down the weight of this bracket as shown here, and we could cut down the weight to around 1.8 kilograms. So when we try to make this through additive manufacturing route, we are finding the cost is comparable, and again the cycle time is reduced without compromise in mechanical properties. So this gives a glimpse of how a design for additive manufacturing can result in optimized designs, whereby you can save weight, which not only adds to direct savings, but it also adds to indirect savings in the form of payload gain. So this particular slide here, it shows again another component which we have made in internal 718. It's a nickel-based superalloy. So this particular component, as shown here, it consists of various intricate interconnected internal channels of very fine dimensions, as shown here, and all these are interconnected by way of zero point 0.8 millimeter holes. And this particular component, it is really very much impossible to make through conventional manufacturing route. So we have adopted additive manufacturing for making this component, and this particular image shown here is the computed tomography image of the component that we made through 3D printing route, and we can see that all these features and all have been formed as desired by the designer. So here again, we have characterized this component. We have evaluated the mechanical properties as per ASTM F3055, which specifies minimum guaranteed properties of 920 and 940 MPa yield and about 1240 MPa UTS and 12% elongation. So against this, you can see here the properties achieved are much higher than the minimum guaranteed properties. And we have also done computed tomography mainly to see the integrity of these channels and see all the features have been formed as desired in the CAD model. And this particular image is shown here. It confirms that the component is made as desired. And we have successfully carried out functional testing of this particular component at 973 Kelvin. And this particular component also has been inducted into our program. So this is another case study wherein we have developed a large component of around 400 millimeters diameter. Earlier, this particular dome, as shown here, it used to be made through a closed die forge route. We used to take a input billet of weighing around 60 kilograms, whereas the final component weighs hardly 12 kilograms. So the extent of material wastage is shown here. In case of conventional route is 48 kilograms, and the operations involved are quite cumbersome, and the cycle time involved is also again quite large. And of course, when we talk about the cost saving, when we made the same thing through additive manufacturing route, since you can see here how much is the input material that is going into making this dome. So we are wasting not more than 6 kilograms of material in making the final component using this particular route, with tremendous advantage of reduction in cycle time, and also we are able to save almost 25% cost. So again, we have used this same additive manufacturing route for realizing a component shown here. So earlier, to realize this component, we were making it through forge route, wherein we used to realize forging weighing more than 2.5 metric tons, and the size of the block used to be 117 to 1514 to 2050 mm. So this particular component, when we are machining it out from this particular block, you can see the component weighs only 120 kilograms. So the buy to fly ratio is quite huge. In the conventional manufacturing route, it is around 21. Whereas when we are trying to make this the same thing through additive manufacturing route, we could bring it down to a buy to fly ratio of 3. And this is the component shown here. Earlier, the brackets as shown here in this particular figure used to be made separately and then fastened onto this particular component to realize the assembly, whereas now we are uh, integrally making these brackets as a part of the grid pin through 3D printing route. And this particular activity has been done at Shiaki, USA. And this is the actual component that has been made through additive manufacturing route, wherein we could reduce the cycle time again to less than 20 days against 80 days, which used to be the conventional cycle time. And you can see here the part count also we have reduced from 5 parts to a single part. So this gives us improved reliability. When we talk about space applications, reliability plays a key role. It is very important to have all our systems reliable. And also you can see assembly of all these things is not involved because we are printing it as a single component. And here again we could have a tremendous cost savings of more than 25%. So we have done thorough characterization of this particular component. So as desired, the chemical composition of this particular component was evaluated as shown here. You can see that we have used titanium alloy filler wire of 3.2 millimeters diameter. Here you can see a peculiarity in the filler wire that is used. It is Ti7 aluminum 4 vanadium, whereas the desired chemistry, you can say here, the nominal chemistry of aluminum is 6%. So being a process which is carried out under high vacuum, there's bound to be some aluminum losses. So to compensate that aluminum losses, we are going for use of a higher composition of aluminum filler wire as shown here, Ti7Al4V. So after this aluminum losses, we are seeing that the achieved chemical composition in the component is within this desired specification range. So after losses, we can see that required aluminum alloy composition is achieved. And this is a microstructure which shows a fully transformed beta microstructure. And we have carried out extensive tensile testing and mechanical property evaluation. So these are the desired properties or the specified mechanical properties. So against this, we could get the mechanical properties comfortably with elongation ranging from 10.3 to 17.3%, and yield strength ranging from 859 MPa to 957 MPa, and UTS ranging from 932 MPa to 1001 MPa, and the fracture toughness again 70 MPa root meter, we could get values ranging from 106 to 112 MPa root meter. So this particular component made through additive manufacturing route also has met the desired mechanical properties specified by the designer. So we are able to induct this component also into our program. So as I was mentioning in one of our slide, DFAM plays an important role in designing weight optimized components for space applications. So we have carried out DFAM on several components. So here again, one such component is a body component in titanium alloy Ti6L4V. So 24 such numbers are used in each flight. So when we carried out a design for additive manufacturing, we could design the component which weighs only 2.5 kilograms. So it is effectively resulting in 31% weight savings, and it directly translates to a cost saving of around 72 lakhs. So once this design has been verified, we have carried out stress analysis, and we have carried out simulation of this particular component, and we see that it is definitely 3D printable. And once we do the 3D printing, we will subject it to functional qualification before inducting into our flight applications. So, having shown a few case studies, I would like to also talk about what are the opportunities in metal additive manufacturing. For metal additive manufacturing in Indian space program, we are looking at industries both within India as well as worldwide to come forward and develop these components for our applications. So as I already talked about, this is one example of a dome for gas bottle applications, which we have already developed through electron beam additive manufacturing route. And we can also look at wire arc additive manufacturing route for making this particular component. And we are also looking at very large size components in titanium alloy Ti6L4V for our propellant tank applications. of around 1.2 meter class components. Again, we are looking at electron beam and wire arc additive manufacturing route. As shown here, these are few components developed worldwide by reputed agencies who are working on these technologies. We are also looking at rings of the same class through these routes. As I had already shown in my case study, we have already developed this grid fin for crew escape systems for our human space program through electron beam additive manufacturing route. And we are also looking at companies or parties who are ready to do serial production of such components through additive manufacturing route. We are looking at development of copper nozzles through either cold spray additive manufacturing route or DED routes. And again, we are looking at large size titanium and Inconel components, which are very complex in nature. And we are trying to effectively save the cycle time and cost of making these components by adopting additive manufacturing. So going forward, we are also looking at development of bimetallic joints through directed energy deposition, especially in the area of titanium stainless steel or stainless steel Inconel or Inconel copper and copper SS stainless steel kind of combinations. So this is one example of a nozzle which have been developed by other space agencies. We are also looking at functionally graded materials for our reusable launch vehicles, such as aluminum, bronze, and stainless steel SS316L combinations. We are looking at development of aluminum and titanium aluminide sandwich honeycomb panels for our satellite applications, mainly for saving the weight. And these are few typical examples of how our sandwich honeycomb panels look like, and we are trying to adopt additive manufacturing for developing these components. We are also looking at development of Inconel 718 spheres or hemispheres to release oxygen storage gas bottles for our human space program. And this particular components also we can develop both through DED and laser powder bed fusion process. We are also looking at large size aluminum components of the class of around 3 to 4 meter class, either through cold spray additive manufacturing or additive friction stir deposition or wire arc additive manufacturing routes. So these are the glimpse of opportunities that are available in metal additive manufacturing for development of components for our space program. This, of course, this list here shown here is not exhaustive. This only gives a glimpse of different items which we plan to make through additive manufacturing route going forward. So to conclude, we have seen additive manufacturing is a disruptive technology that has been growing exponentially worldwide, and it has become a cost effective, and it has been gaining more popularity when we talk about applications for space sector. And I have also shown there's tremendous potential for replacement of numerous conventional parts or assemblies by additive manufacturing by using design for additive manufacturing for designing cost efficient and lightweight systems for space applications. Of course, when we talk about adopting a new manufacturing route, there are a lot of certification challenges that need to be addressed to accelerate inducting additive manufacturing components, additively manufactured components into our supply chain. In space sector, we are addressing this by taking up different case studies and carrying out certification or qualification of the components. And it is not possible to use most of the conventional NDT techniques due to the characteristics of the material or the shapes that we are trying to make through additive manufacturing route. So we are also looking at adopting different NDT techniques available for qualification of the components made through additive manufacturing. And also we are looking at developing various critical and complex components. Already we have seen many of the space agencies have qualified and inducted them into their program. So we are also looking at making this complex and critical components, assemblies or sub-assemblies of various sizes through different additive manufacturing routes into our program. So with this, I conclude my talk, and I would like to acknowledge my management for giving me the opportunity to share my experience in this forum. And I also thank the organizers of the second international conference on 3D printing and additive manufacturing, and my colleagues at VSSC and collaborators of VSSC in metal additive manufacturing. And I also thank the audience for a patient hearing. So thank you. So I hereby conclude my talk.
Thank you, Dr. Ms. Anil Kumar, for your presence and presentation. Does anyone having any queries?
Hello.
Uh,
Yeah, hi.
I, yeah,
Uh,
yes, Dr.
uh,
Efron, you can ask your query.
Thank you, Doctor, for you have a wonderful talk. You explain very well about metal additive manufacturing. So my two questions. The first one, you have mentioned about the metal printings. So in metal printing using SLM and EBM techniques. So have you using EBM printing some parts like the stainless steel? So second question is you have focused on research on the space additive manufacturing. So have you printing some parts for space solar power
Yeah,
stations?
okay. I got your question. Yeah, to answer your question about the first one, you were asking about electron beam powder bed fusion, if I'm right.
Yeah, yeah, yes, yes.
Yeah. In fact, we are looking at developing a few components in both superalloys as well as titanium aluminides through mainly through electron beam powder bed fusion. So we have been having discussion with some prospective parties who have the facilities, and we are looking at developing some honeycomb sandwich panels in titanium aluminide for our space applications. And coming to your second question on applications for solar panels. Yes, in fact, in Indian Space Research Organization, we have different centers working on launch vehicles and also on satellite applications. So there's another center in Bangalore. It is called as UR Satellite Center. So they are responsible for developing components for satellite applications, and of course, I've seen they have plans of making this components for solar array deployment mechanisms and all through additive manufacturing. Yes, there are activities going on.
Okay, thank you.
Yeah.
Thank you, Dr. Efron, for your feedback. Does anyone having any further more queries? I hope there are no queries. Once again, thank you for your presence and presentation, Dr. Anil Kumar.
Yeah. Thank you so much.
Okay, now let's move on to the next presentation is from Dr. Tayaba Bari from ComSat Institute of Information Technology, Pakistan. Hello, Dr. Tayaba. Are you ready with your presentation? We are unable to hear your voice. You're not audible, Dr. Tayaba. No, you're not audible. Can you please check your microphone settings? We're unable to hear your voice. In the top right corner in the settings option, please select your microphone which you are using. If you are using any external microphone.
Can you hear me?
Yeah, you're audible now. Okay, now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Okay.
I have made you as a presenter.
Can you see my presentation now?
Yeah, it is visible. Make it as a full screen mode and start your presentation now.
Okay. Hello. Assalamu alaikum. And a very good morning and a good afternoon to the respected fellows from all over the world where you are listening. My name is Taiba Bari and I am from Lahore, Pakistan. I am a PhD scholar of biochemistry in the University of Veterinary and Animal Sciences, Lahore, and a research assistant in Interdisciplinary Research Center for Biomedical Materials. My mentor is Dr. Hafsa Fakhra and she is running a research project on cartilage regeneration. On the behalf of my research team, I am presenting the revolutionizing cartilage regeneration, that is, crafting organs through 3D printed biological scaffolds from decellularized umbilical cord. The contents I have covered in my presentation is a brief introduction about the osteoarthritis, then the stats of the disease, then the existing treatment approaches that are used so far, Then the advantage of using umbilical cord over the other tissues and extracellular matrix in tissue engineering, the research gap that is present, and then the methodology I have followed in my research, then research and discussions, conclusion, and future perspective. So, first of all, a brief introduction about osteoarthritis. Osteoarthritis is a degenerative disease affecting more than 528 million people worldwide, resulting in the deterioration of the whole joint. This whole joint includes the peritubular muscles, capsules, the ligaments, the fibrous joint capsule, articular cartilage, subchondral bone, and each and every component of the joint. The symptoms often develop slowly and worsen over the time. The common symptoms include pain, stiffness, tenderness, loss of sensibility, bone spurs, and swelling. The factors that increases the risk include older age, gender, obesity, joint injuries, genetics, and any metabolic conditions. So, if I talk about the stats of osteoarthritis, then World Health Organization estimates that osteoarthritis occur in 9.6% of men and 18% of women with the age 60 years or more, which make it a highest ranking disease among other musculoskeletal diseases, impairing an individual mobility. So, if we talk about the type of osteoarthritis, then among hip, hand, and knee osteoarthritis, you can clearly see that the peak of knee osteoarthritis is more frequent or common. And the cartilage regeneration using umbilical cord tissue, which is considered as a waste after the delivery of the child, will provide a strategy for biomimicking the native cartilage by providing the similar nutrients and microenvironment. The existing treatment approaches that are used are: as the articular cartilage tissue has no or a limited number of vessels, therefore after the damage it cannot regenerate itself. The arthroscopic procedures that have been used to repair the cartilage are autologous chondrocyte implantation, that is a procedure in which the patient's own cells are excised from the body and grown ex vivo, and after certain growth period they are implanted back into the patient. The next is a microfracture, that is also another arthroscopic procedure in which small holes are first created at the base of the bone. These holes allow the passage of blood and other tissue repairing proteins in the injured area, thereby regenerating the tissues. And next is the cartilage transplantation, in which the cartilage is transplanted. However, most of them are failed and lead to further damage. Therefore, research in regenerative medicine keeps on providing new strategies for the treatment. The combination of cells and biofactors along with the scaffold is the optimal approach which can give rise to cartilage regeneration. The advantage of using umbilical cord over the other tissue. Getting access to ample tissue in order to fabricate a scaffold is of critical importance. Similarly, to get enough of the cartilage tissue is a limiting factor. The alternative approach is to use the tissue which has a similarity to cartilage and which should be available all the time. The composition of Wharton's jelly, a part of umbilical cord, consists of low number of cells and rich in hyaluronic acid, glycosaminoglycans, and collagen, making it a hydrated tissue which resembles to the cartilage tissue. In addition to that, cartilage is free from blood vessels and neurons. This feature is also a similarity between cartilage and umbilical cord. The tissue is also discarded as a waste after the baby is born, so it relieves the ethical concern if it will be used for research purpose. The role of extracellular matrix in tissue engineering. A variety of synthetic and natural scaffolds such as gelatin, collagen, chitosan, polylactic acid, agarose, alginate are used for signaling and responsive microenvironment. However, to provide biochemical signals for the cells to differentiate in a host environment, the use of biomimetic tissue-specific scaffold is an emerging trend. Decellularization of tissue is a novel method in order to produce the extracellular matrix. Scaffolds derived in such a way contain a complex mixture of structural and the functional proteins such as collagen, elastin, glycosaminoglycans, and fibronectin. ECM from the decellularization of the native tissue holds a great potential in medical industry of tissue engineering field. The research gap. The research gap present between the existing bioink is due to their biodegradability, their hydrophilicity, porosity, mechanical strength, and viscosity. And the limitations of these pre-existing bioinks are due to the resemblance of the created constructs with the natural tissues. Compositional diversity and architectural complexity with the native tissue has not fully achieved yet. The novel therapeutic approach that we are using in our project is that will provide a high degree of automation, structure similarity, architecture fidelity, reduced immunogenicity of the created construct, and this all can be achieved by the fabrication of 3D biological scaffolds from umbilical cord tissue. The methodology I have followed in my research is first is the step of the decellularization in order to get the extracellular matrix. This was achieved by several physical and the chemical and biological methods. The next was a confirmation of decellularization on the basis of DNA and on the basis of extracellular matrix. The DNA was evaluated by molecular means and histological means by running on 1% agarose gel and by histological means by DAPI and hemotoxin and eosin staining. The next, the conservation of extracellular matrix was quantitatively and qualitatively estimated by LCM blue staining and Mason's trichome staining and by hydroxyproline assay kit. The next, the product we have obtained so far was the extracellular matrix that was rich in the collagen and glycosaminoglycans. Next, this product is solubilized in order to create the bioink, and this was achieved by acid and pepsin digestion. The next step is the characterization of myelin by FTIR and scanning electron microscopy. Next was the optimization of the bioink. The bioink was optimized on the basis of biodegradability, hydrophilicity, the swelling ratio, porosity, viscosity, and rheology. After this, once the bioink was optimized, then it will further proceed for the 3D fabrication of biological scaffolds, and these biological scaffolds were then evaluated in vivo and in vitro. For in vitro, LMR blue assay was performed, and the bone marrow-derived mesenchymal stem cells were used, and they were checked for their cytocompatibility and biocompatibility. The next, these scaffolds were implanted in the 3D biological scaffolds, and after 7 weeks, models will be evaluated microscopically and macroscopically. Microscopically, LCM blue staining was used to confirm the presence of the collagen, and macroscopically by the appearance on the basis of a scoring system, that is by ICRS, that is International Cartilage Repair Scoring System. Uh, in this way, we can achieve a regenerated cartilage. These are the results and the discussion of my research. First, we have taken the umbilical cord from the patients undergoing C-section or the normal delivery. Then this umbilical cord was cut into small pieces and they were passed through several freeze-thaw cycles and the osmotic shock. Then they were processed by the detergent-based method, that is sodium rhodecyl sulfate. After this, the DNA content was checked by nanodrop or by running the gel. Here you can see a clear-cut difference between the before and after decellularization procedure. The results of the decellularization was confirmed by molecular and histological means. The decellularized umbilical cord is free from cells, cellular debris as run on the gel. You can see that the native umbilical cord contains a significant amount of the DNA, whereas in the 1% STS treated samples, there is only a small amount of DNA that is present and can clearly seen when run on the agarose gel electrophoresis. The next is by the estimation through histological methods, that is by hemotoxylin and eosin staining. Hemotoxylin precisely stains the nuclear components including the heterochromatin and nucleoli as blue, while eosin stains cytoplasmic components including collagen and elastic fibers as pink. The Duby staining is used as it is a fluorescent stain and it binds strongly to the adenine thymine rich regions in DNA and it stains it blue. Here you can see the before and after the decellularization process of human umbilical cord tissue. The next was the confirmation of the extracellular matrix preservation. It was further preserved, checked by qualitatively and quantitatively. Trichome staining is used to visualize the connective tissue, particularly the collagen. In a standard Mason trichome procedure, collagen is stained blue. That is, it is the basic component, so it will react the acidic component of the strain, and which retains it into the blue color. Here you can see the results of the hydroxyproline assay, in which the native and 1% SS treated sample both contain a significant amount of collagen. The next was the conformation of glycosaminoglycans. They were confirmed by dimethylmethionine blue assay, qualitatively and quantitatively by LCN blue staining. It stains the acidic polysaccharides such as glycosaminoglycans to blue or light blue color. Qualitatively by LCN blue, the results are in this way. You can see that where is the glycosaminoglycan is present, it will stain it into light blue color. Similarly, dimethylmethylene blue assay is used to quantitatively estimate the amount of glycosaminoglycans present, and it is 1.1 microgram ml of glycosaminoglycans was present. The next step was the solubilization of the extracellular matrix to biotin by acid and pepsin digestion. Where the extracellular matrix was first lyophilized, it is then grounded into powder. This powder was disinfected by ultraviolet radiations and solubilized at acidic 2.2 pH. Basically, we have used an enzyme that was a pepsin in order to digest, and pepsin cleaves the telepeptide region in the collagen. The next was the preparation of bioink. After the solubilization, the solution is neutralized to physiological pH, that is 7.3 to 4, and it was incubated at 37 degrees Celsius, and the viscous solution of bioink was formed. The next was the characterization of this bioink solution. Here you can see the spectrum of chitosan depicts characteristic absorption bands at 3350 to 2878 per centimeter that attributes the hydroxyl and the methyl groups. Similarly, collagen displayed mainly bands at 1650, 1560, and 1235 per centimeter. That is the characteristic of amide 1, 2, and 3 bands respectively. The interactions between collagen and chitosan occurs by hydrogen bonds, that is the hydroxyl, amide, and carboxyl group in the collagen are capable of forming the hydrogen bonds with the hydroxyl and amide in chitosan. The next was the bioinks were further evaluated and optimized on the basis of the following parameters. That was the biodegradability by enzyme degradation method, their hydrophilicity by contact angle measurement, their swelling behavior by swelling ratio, porosity measurement by liquid displacement method and by scanning electron microscope. Next was the viscosity and the rheology by visco and the rheometer, and next was the 3D fabrication of biological scaffolds. Viscosity of the bioink. Bioink viscosity increases concomitantly with collagen concentration, and at 37 degrees Celsius, ideal viscosity reported for collagen-based bioink are in the range of 1 to 30 pascals. Bioinks with low viscosity have a low resistance and shear easily, and the molecules flow quickly. High viscosity bioinks move sluggishly and resist deformation. Here you can see as I have used 5 different concentrations of bioink, that is 10, 20, 30, 40, and 50, and as the collagen concentration was increased in these bioinks, their viscosity also increases. The next is the biodegradability by lysozyme degradation test. Bioink should be degradable yet retain enough mechanical properties for a period of time sufficient to regenerate the cells. Scaffold-based bioinks are preferred because their degradation rate is similar to the rate at which the cells construct the extracellular matrix. Here you can see the biodegradation rate after 24, 48, 72, and 96 hours. The next is the porosity of the bioink. Porosity ratio increases with the increase in the collagen concentration, and it again depends on the function or what target we want to achieve from a particular biomaterial. 3D printed structures with incorporated cells require a broad range of pores from millimeter to nanometer scales. Small pores nanometer scale are essential for nutrient absorption retention as well as for the structure support. Middle-sized pores in micrometer scale are desired for cell proliferation as well as the nutrient diffusion. Pores in the millimeter scale decrease diffusion pathways and therefore enhance the permeability of the material and accessibility of the embedded cells. It will be determined in such a way by the collagen concentration. Here you can see as the concentration is decreased in the biomaterial, their porosity ratio increases. I will conclude my presentation by that the results highlighted that a collagen-based bioink is successfully prepared and can be used as cartilage substitute and a suitable candidate for 3D bioprinting. The results revealed that biomimetic construct is promising biomaterial in terms of properties such as high hydrophilicity and water absorption capacity, which could be used in applications such as tissue engineering and regenerative medicines. We are looking forward towards the fabrication of these 3D printed scaffolds, then the cartilage differentiation markers, and the cartilage differentiate potential by chondrocytes. Um, Last but not the least, I want to acknowledge as that I have been working on this topic for a long time and different hurdles has been crossed by my way to achieve these results. I extend my heartiest thanks to my mentor, Dr. Hafsa Fakhra Ikram, and Dr. Syed Qasim Raza for their role in making me understand different principles and the research techniques that made this project works a success. This endeavor would not have been possible without my fellow researchers, facilities, and the working environment of Interdisciplinary Research Center in Biomedical Materials, COMSETS. Thanks. This was all from my side. Any questions?
Thank you, Dr. Tayaba, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you,
Thank
Doctor,
you.
for your presence and presentation. Now, let's move on to the next presentation. Is from Dr. Shifan Kande from Dubai Medical College for Girls, UAE. Hello, Dr. Shifan. Are you ready with the presentation?
Yeah, hello, I'm ready. Can you just give me a
Okay,
link to
now I'm
share?
making you as a presenter. Kindly click on the screen button to share your screen, please.
So it's for optimize for video or include go to interface.
No, your screen is not visible yet. Can you please give your permission to share your screen?
Sharing screen permission to capture screen. Okay, just a second. Just a moment.
Hello everyone, let's wait a few more minutes to join Dr. Shifan to avoid technical issues.
Yeah, hi. I was accidentally thrown out of the session. Can I get the share permission?
Yes, I have made you as a presenter now. Kindly click on the screen button to share your screen, please.
Can you share my screen now? Can you see my
Yeah, we
screen?
can see you. Yeah.
Just a second. Yeah,
You
now?
can open your PowerPoint presentation and start your presentation.
Can you see my presentation now?
Yes, can you make it in a presentation mode?
Yeah. Yeah, so greetings everyone. I'm Dr. Shifan Khande. I'm an associate professor and director of e-learning and digital innovation at the Biomedical College for Girls. So my topic of presentation today will be exploring the synergy between 3D printing technology and embryological teaching and research. So I will carry this session on from where all you stopped. It was amazing to see you all from ISRO and from Pakistan and actually doing the printing thing. And so my part will be how we will be using these printed material from your hard work and putting it into teaching and research. So, brief introduction about my talk. I will be talking about some traditional embryology educational methods that were used in research and education till now, some of 3D printing softwares and models which are currently used in teaching and in research, and what is the importance of these innovative education tools, especially in medical sciences. And if you have any discussion points, any of you has experience in such integration technology, we will be talking about it. So for traditional embryology education, I don't know how many of you are from medical stream. It's very difficult for researchers and students to get hold on embryological models for their research and study. So 3D printing came as a boom to excel this because it's very difficult to understand at each level and each week a level of development what is happening around. And if you don't know the normal steps of development and the steps of development, the abnormalities and variations cannot be understood well in the end. So here we are at the intersection of 3D printing technology and embryological research, which sounds promising for biomedical science, especially because of lack of tissue and ethical issues in receiving these embryos for study. So just a comprehensive outline on some of the study modes or tools we've been using, and keeping ethical implications also into consideration, how 3D printing is helping us in going ahead with it. So primary objective, as I said, it's just revolving around the 3D printing technology, which I'm sure all of you, most of you are the experts in the technology part. And me as a practicing physician and educationist and into digital technology, we are taking it to the next level of how to use it. So just we went through some scoping review of articles which are present and currently what models we have at our institute for study. So I will take these objectives ahead and move forward. So like we took from literature review and case studies and whatever is available on the internet, a lot of studies, but actually some are in experiments, some are available. And what we get in the end is like we could only extract some 3D printed models, especially for cardiology, and we used it for teaching. So as I said that such researches and teaching methodologies, they have a potential to revolutionize the biomedical science research and teaching, and it unlocks new avenues for more tissue engineering endeavors and regenerative medicine especially. So our step to at this point is to pilot study the need of these 3D printed models and how we can use it in our regenerative labs and in the developmental biology research processes. Right. So innovative solutions for organ transplantation will come through these research, and personalized medicine will be benefited if we have a good embryological background for teaching and research. Right. So what we found out from these companies who are helping us, they say that they create, actually we are not creating, we are procuring and we are using in teaching from these voxels which are like you are the experts there, you know how these vertexes are used, and these meshes which allow the visualization and the ability to design color and texture and animate these models for us. So some of the models that we use for aiding in teaching embryology and surgical training, we've been exploring these. So this successful software which came to us as Blender, open source 3D modeling software, which our procurement like chain they have these companies which use these technologies, and as I said, we are just purchasing at this moment and not creating anything, and we are using this for teaching purposes. So this sounds very promising for our teaching and research. The other softwares we came to know about is a list of these 10, like Autodesk Maya, Cinema 4D, ZBrush, Rhino, Blender, Modo, Lightwave 3D. So all animations and modeling and sculpting can be done through these softwares. And we are looking for experts in this field to help us in taking the research ahead with these. Right. So why we need such type of softwares and why we need the developmental models? Because as I said, that we are only focused on honing the skills in surgery and to know how to manage various congenital malformations in the human body. So these are pictures of some normal section of heart and normal, if you can see the foramina there. So students get to know the normal. They need they have these models in front and they work on these, and they know the normal development, which is very difficult to learn from the videos. So once they have in hand, they get to know the actual location of structures and actual developmental process. This is another picture of the heart looping, which is very difficult to understand, and these 3D printed models are helping the students to understand, especially the looping of the heart and the formation of the chambers. They do it and they touch them uh, to know the actual step. So this is a picture we received. It's for different skeletal and different models which are present, and we procured one to show at which level how the nervous element and blood vessel and nervous system develops. So what students are learning and researchers are learning with these type of models in hand and learning by these, we see that the tactile learning experience, as I said, unless they don't touch the structure, they don't feel and they don't remember. So it's a hand-on experience which understands which helps in understanding and retention of complex concepts. So improvement in spatial understanding will be like the three-dimensional nature of these models, which helps the students to visualize and comprehend the spatial relationship between different embryonic structures. Like I showed you, the nerve elements are separate, the vessels are separate, the bony elements are separate. So they are especially valuable in understanding the complex anatomical arrangements. Then we go for realistic anatomical representation, yes, because they are printed from they are created in highly detailed and accurately from the anatomical models, and they are replicated, and the intricacies of the embryo are retained. So they are customized, and they are taken as an authentic source of learning. Reproducibility for this will be that once it's created, it can be replicated easily by 3D printing. The printer remembers, and we can reproduce multiple copies of the same structure that we want to. And interactive teaching tools, it with the software, especially once we have it and we have the AR and VR features enabled for the particular model, we can take it into a next level of engagement as an interactive learning tool in the 3D software, not on the model but with the software. So students stay engaged and motivated, and they by hands-on practice they learn more. And when we talk about accessibility. So we say that the digital files which are used to create these 3D printed models, they can be easily shared and accessed online. So wherever the students are and the facilitators are, they can have a review of the models inside classroom, outside classroom. So reinforcing the understanding of embryological concepts can be taken part. So like I said, we integrate it with technology, the printed models. We have the AR cameras, and we can have a uh, right now we are not having our own software, but we have procured, so we can click the picture and convert it into AR, and we can keep our own repository for such 3D printed materials. So for clinical practice, as I said, we can uh, take use of malformed specimen and how they look like, and how the surgeons can hone their skills on these abnormalities or variations. That sounds very promising. So these are realistic 3D printed models, and they prepare the students for clinical scenarios, and understanding the embryological development and the practical part of it. So we believe that in incorporating these 3D printed models in embryology teaching and research especially, it will help in enriching the learning process by, in nutshell, by giving a hands-on and a virtual appealing and customizable education resource. Right. So these are one of the few, like one or two benefits that we have. There are many, but the benefits are, like we said, that it's impossible to learn from the textbooks or images unless we have a model in hand, and a realistic model in hand. So 3D printing comes as a boon, and low cost, as according to the material we will use. We can customize our models from the company, but if it's tissue related, then I know it's going to cost us a lot. So to conclude with this, this 3D printing, especially, just having the experts here, so this is a very amazing opportunity, and these techniques are highly versatile, and we can create the models, and we can help in getting the animations and videos. Especially as educators, it will help us in enhancing the learning and training experiences, and especially honing the surgical skills, and uh, especially in cardiac embryology. I told you that these defective models that we show them, and the VR associated with it, it helps in immersive visual and tactile experiences. So this is from the educational side of it, what you people are doing. So we want to dive deep in, like we said, we want to go into embryological research related to regenerative medicine, and we want to see how possibly technology can be incorporated, and area of further research related to education, not as a replacement of some defected piece or a diseased organ, but we are looking forward for the research use and in educational use, and how we will integrate such 3D softwares and 3D printed materials in our educational curriculum. So, so we want to create a set of educational suggestions for the masses and for the academia, and we will give recommendations for such further research if ethical approval is there for the tissue to be used in this. But 3D hard material that is available, that is doing wonders, and people are using it for teaching, learning, and research. And as academics, I said that we are calling for action to adopt such technologies, where there will be lots of hand-on and lots of clinical exposures with help of experts like you in building such models for teaching and learning. And I think this is gist of our aim, what we are going to do with all these models which I said are available, and how education and research is going to be benefited from this. So like I said, the audience has few experts. If we can share some thoughts, like what is the feasibility of implementing these recommendations in educational context especially, and that would be wonderful.
Thank you, Dr. Shifan, for your presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Dr. Shifan, for your presence and
Okay,
presentation.
thank you. Thanks a lot, everyone.
Okay, now let's move on to the next presentation. Is from Dr. Raymond Ushaw from the Federal Polytechnic from Nigeria. Hello, Dr. Raymond. Are you ready with your presentation? Hello, Dr. Raymond. Hello, Dr. Raymond. Are you ready with your presentation? Hello, Dr. Raymond. Hello, Dr. Raymond. Are you ready with the presentation? Hello, Dr. Raymond. Can you please unmute yourself? Hello, Dr. Raymond. Hello, Dr. Raymond. Can you please unmute yourself? Okay. Now, I think Dr. Raymond is not responding. Now, let's move on to the next presentation. Is from Dr. Nafishe Behere from Tarbiyat Modares University, Iran. Hello, Dr. Nafishe. Are you ready with the presentation?
Hi, do you have my voice?
Yes, your voice is audible now. And now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Okay, just a minute.
I have made you as a presenter.
Yeah, I know, but just a minute.
May I know which device you are using?
Now, can you see the screen?
Yes, your screen is visible. Can you make it as a presentation mode and start your presentation in full screen mode? No, beside the Zoom,
This is
beside the
the
Zoom, you
PDF
have the
file.
option to full screen.
No, but this is the PDF file, so
Yeah,
it couldn't be
PDF only. You
better
can
than
make
this.
it as a full
Yeah.
screen. In that, just make it as a fit screen. Beside 47, you have one option. It's a drop down. 47 on the top.
Okay, fine.
On the top, we have
Is that
no, no,
fine?
no. Beside that, you have a option, right, to a drop down. On the top, yeah, the percentage of the zoom, and beside that, beside the 55. Beside the 55. I'm saying the beside the zoom option, the percentage option. No, no, top in the middle of the screen.
This one
No, in the
and
middle of the
this
screen, middle. The 55 is there, right? 55 in the
okay.
middle.
I know. Is it
Yeah,
5?
beside that, the next one, the drop down is there, right? Yes, the next one, the next option.
100?
Yeah, that the next option, not 100. Don't choose that one. The beside one, please select that. Is it
Oh,
there is a
this one?
paper? Yeah. In that, please fit the screen. Select full screen,
Oh,
okay? Or
the first one
the
fit
read mode or
to
anything. You can choose any read mode. Read mode
is that
there.
5?
Okay, you can continue. In that, please select read mode. If not possible, you can continue in the read mode.
Okay.
Okay, you can
Okay.
continue your presentation.
Good morning, ladies and gentlemen. Before I start, I would like to thank the organizing committee for giving me the opportunity to have my presentation in this Congress. My name is Nafisa, and I'm the associated professor at Tarbiyat Mudaris University in Iran. My main focus is on bone and cardiac tissue engineering. And in recent years, I have worked on antibacterial materials, mainly graphene-based materials, to make the electroactive scaffolds for tissue engineering. Now, let's start. Just a minute. So today I'm here to talk about graphene-based materials for cardiac tissue engineering. If you look at the statistics, you can see that cardiovascular diseases are the primary cause of death worldwide. Uh, you know, every 40 seconds in the US, one heart attack will happen. That means 30% of all deaths worldwide continues to be cardiovascular diseases. Among cardiovascular disease, myocardial infarction stands at most. It happens when we have complete or partial blockage of coronary arteries, and it causes cardiomyocyte death, raises immune system, and leads to the fibrotic tissue formation. And if it doesn't get proper treatment, ultimately it leads to the heart failure. Despite pharmacological and surgical intervention, heart transplantation still stands as a gold standard. However, this procedure is accompanied by donor shortage and the risk of graft rejections. Therefore, we are switching to the innovative treatment. Cell transplantation, as one of the innovative treatment, has a potential to use to regenerate cardiac tissues, but still it has some limitations like low cell engraftment and low cell survival. On the other hand, however, tissue engineering that is helping to promote the therapeutic efficacy of stem cell-based therapy. It could help us to have the high cell retention and improve the cell maturations. Now, when we are talking about cardiac tissue engineering, electroactivity sounds really important. That is because it is the essential requirement for the application of materials in cardiac tissue engineering. So there are ranges of electroactive moieties that can be used in the structure of the scaffolds, from carbon-based nanomaterials, gold-based nanomaterials, conductive polymers, and so on. But among a wide range of electroconductive materials, graphene-based nanomaterials or GBNs are promising for cardiac tissue engineering. That is because they have outstanding features like high mechanical strength, electroconductivity, biocompatibility. They could provide high specific surface area, and they have the low cost and scalable fabrications. In medicine, they have outstanding features from drug delivery, gene delivery, biological sensing, to specifically tissue engineering, which help us to provide high angiogenic properties, anti-inflammatory effects, and they can scavenge free radical species. Now, let's talk about angiogenic properties, which is one of the important properties made by the help of GBNs. You know, angiogenesis is a crucial step in the formation of a new blood vessel from the vascular networks that already exist. This is an important step for a variety of physiological and pathological processes, including embryonic development, wound healing, atherosclerosis, and ischemic heart disease. There are some stages in angiogenesis, from endothelial cell proliferation to cell migration, and finally capillary tube organization. Uh, Someone has his microphone. Could you please close your microphone, Dr. Raymond? Thank you. Now, why is angiogenesis important when you're doing cardiac tissue engineering? You know that when MI happens, there is inadequate blood supply to the myocardium, which is a cause of myocardial cell death and leads to the abnormal left ventricular remodeling. So if you could develop new blood vessels following MI, then it would be very helpful to the ischemic myocardium to regain its blood and nutrient supply. Numerous studies have illustrated the potential angiogenic potential of GBNs. Let's see, our group previously developed conductive scaffolds by chemically coating reduced graphene oxide over collagen scaffolds. On the right above, you can see the different scaffolds we made being coated with different concentration of reduced graphene oxide. What we observed was the increased viability as a result of the RGO inclusion. On the left, you can see the morphology of the endothelial cells, which were seated on over the different scaffolds. Also, the expressions of cardiac genes was statistically increased compared with the corresponding counterpart without RGO. Here in this screen, you can see the gross morphology of the scaffolds, which were implanted subcutaneously after 2 and 4 weeks. So RGO coating scaffold exhibited more sprouting vessels than the collagen one. Also, we perform immunohistological assessment to find out the microvasculature formations with VEGF. The results showed improved cell infiltration within the electroactive scaffolds and confirmed their angiogenic potential due to the presence of reduced graphene oxide. Now, what is the mechanism of angiogenesis? So, you know, graphene oxide could activate the pathway of focal adhesion kinase via integrin-mediated cell-ECM contacts. This could describe the angiogenic mechanisms of graphene. You know, when there is an increase in fibronectin adsorptions on GBNs, then the cell ECM interactions will enhance, and then ultimately we will observe the upregulations of the secretion of angiogenesis growth factors such as VEGF, HGF, and FGF. Graphene oxide, on the other hand, has two roles. dose. If we consider the low dose of graphene oxide, then through Ross formation and nitric oxide signaling, then it will affect the angiogenesis. On the other hand, if we use the graphene oxide at high dose, it could have the opposite effect as an anti-angiogenesis factor. Another property of the graphene-based materials are antioxidant properties. You know, when myocardial infarction happens, there is an increase in the high oxidative stress, which could lead to the myocardial dysfunction. This high oxidative stress could target DNA, proteins, and cell membrane and causes death of myocardial and vasculature within the cells. And ultimately, we will have further organ damage. So researchers have shown that if we could use the biomaterials that is Ross scavenging, then we will be able to remove excess Ross and we can preserve cardiomyocytes and enhance cardiac performance. What is the mechanism of GBNs to be used as Ross scavenging materials? There are many mechanisms, but here I have sorted just 3 of them. These are hydrogen donation from the surface functional groups, radical adduct formation by sp2 hybridization, and the chemical reduction of graphene oxide to reduce graphene oxide. In one of our recent research, we prepared a novel cardiac patch based on alginate being coated with different concentration of reduced graphene oxide. Here you can see the macroscopic images of the prepared scaffolds. As the concentration increase, the color get darker. Obviously, by increasing the concentration of RGO, the cell viability, the endothelial cell viability increased. Also, on the left, you can see the morphology of the endothelial cell being seated over the scaffolds. You see that they have good attachment on the surface of the scaffolds. In this research, we evaluated the expressions of VEGFR2 at both mRNA and protein levels. What we found was upregulation of VEGFR2 at both mRNA and protein levels. That confirms that RGO coating could significantly increase the angiogenic capability of alginate hydrogel against endothelial cells. Also, in that study, we assess the rate of the growth rate of 3 species of bacteria in the presence of the scaffolds, and you can see that the scaffolds with the higher graphene oxide could eradicate the rate of the bacteria. And also we proved that the prepared scaffold, especially one with having RGO, could have antioxidant capability. Here is the result of the in vivo assay. You can see the gross morphology of the scaffolds, and the scaffolds were subcutaneously implanted, and after 1 and 3 weeks, the black scaffolds are the RGO containing scaffolds, and the white one is the alginate scaffold. We assess the expression of CD31 and also alpha SMA to assess whether the RGO addition could have a beneficial effect for the expression of angiogenic factor. Hopefully, with the histological evaluations confirm that the enhanced vascularization properties of coated scaffolds could be observed after subcutaneous implantation. Another property that the GBNs could provide for in tissue engineering, especially in cardiac tissue engineering, is cell proliferation and differentiation. One important thing to be considered is that in the human heart, there is a limited regenerative capacity. You know, the reason is because cardiomyocytes leave the cell cycle shortly after the birth, and they can be replaced by maximum 2% of the adult heart cells per year. So if you could stimulate the cardiomyocyte to proliferate, then that would be a good approach to trigger the healing process. So promoting the cardiogenic differentiation of stem cells is another supportive approach in heart tissue regeneration. What is the mechanism of GBN's action for cell proliferation? You know, GBNs could enhance tissue development and could have impact on cell differentiation via various tissue types. These are not only cardiac muscle, but also neural bone, neural tissue, and bone tissues. The reason is GBNs could have non-covalent contact with biomolecules, and through this contact, they will increase the accessibility, protection, and they could trigger cell differentiation. Another mechanism is the activation of mechanosensing pathway. They affect the cytoskeleton rearrangement and in turn could increase electrical activity of cells. And then if the electrical activity increases, then the cell differentiation will be achieved. In one of our researchers, we made 3 graphene film using chemical vapor deposition, and we did some kind of experiments to make comparison with using only 2D graphene film. You can see the SCM images of 3D graphene. As other previous researchers, our previous researchers, on 3D graphene film, the cell viability increased compared with the 2D one and the tissue culture plate. Here you can see the morphology of the cardiac cells over the prepared graphene film and the 2D film. Also, the increase in the cardiac gene expressions was observed on 3D graphene film compared with other prepared scaffolds. The fourth property that today I'm going to talk is the antibacterial properties. As is obvious, cardiovascular implants can develop infection-associated biomaterials and biofilms, and infective endocarditis is a leading cause of illness, especially in the elderly. There are 3 species of bacteria which involves in endocarditis. Among them, SROs is the leading cause of acute IE, whereas the other 2, one that is E. coli and Spirogenes, both of them are the cause of endocarditis in people which having prosthetic mitral valves. History. What is the mechanism of action for antibacterial? The graphene antibacterial mechanism is based on physical and chemical interactions. Graphene has sharp edges which can disrupt the cell physically, and wrapping bacteria with the graphene nanosheet and also the photothermal ablation of bacteria with laser energy are also part of the physical mechanism. What about the chemical interaction? We can say that the oxidative stress that causes as a result of a GBN's presence, so it could damage the DNA, mitochondrial, and other organelle within the cells, and ultimately leads to the death of the bacteria. In one of our research, we evaluated the We made the electroactive scaffolds by chemically coating reduced graphene oxide over collagen scaffolds, and we evaluated the antibacterial and other biological characteristics of the scaffolds. On the right, you can see the structures of the prepared scaffolds, which are porous, and they are having interconnected pores. Expressions of cardiac genes and cell adhesion and proliferation was statistically increased compared with other scaffolds. Here you can see the antibacterial evaluations of the electroactive scaffolds against 3 species of bacteria, and the T here you can see is the electroactive scaffold, and you can see the inhibition zone, the observable inhibition zone. Also, we from FESCM images of the bacteria attachment to the scaffold, to the electroactive scaffold, you can see that against E. coli, almost nothing has been attached over the scaffolds. Another provided properties for cardiac tissue engineering as a result of using GBN is electrical properties. Electrical conductivity seems really important in cardiac tissue engineering. That is because the growth of the growth of the cells, and especially this organ, is really dependent on the electroactivity and the electrical signal propagations. Whenever it happens, there is disruption of blood circulation, and we face cell apoptosis and scar tissue formation, and finally we face cardiac arrhythmia. GBNs could enhance the charge distribution and action potential propagation by facilitating the cell's electrical coupling among the cells. What are the mechanisms of action? I can say that cell-cell and cell-substrate interaction will be improved as a result of using GBNs. Also, GBN could facilitate the cell's electrical coupling by reducing charge impedance and improve charge distribution and action potential propagation. I guess the last property is the mechanical properties. When MI happens, there is lack of proper mechanical support, and the cardiac function will be impaired. So as a result, it results in ventricular dilation, and finally, we will have cardiac remodeling. Mechanical properties are among the most critical factors to be considered in scaffold design. The reason is because cardiac tissue as an alternative contracting muscle is relatively soft but fatigue-resistant cell substrate. From the microscopic point of view, cell substrate could mimic the mechanical properties of the native tissue, and they're more likely to regulate cell differentiations. What is the mechanism of action? There are two mechanisms. One of them is mechanotransduction. You know, cells sense mechanical signals, and within the cell, acting substrate linked to the focal adhesion complexes for mechanical signal transduction. Another mechanism is topography. Genes could create surface roughness, and this could result in overexpression of focal adhesion-related signaling molecules, which results in cell adhesion increase and cardiomyogenic differentiation. Okay, despite promising features of GBNs to be used for cardiac tissue engineering, we are still facing limitations. What are they? We are worried about potential risk and cell toxicity, which is caused by the presence of GBNs. We are worried about physical and chemical interactions of the GBNs with the cell membrane, whether they are inducing oxidative stress in the cell, or they're interacting with cell genetic materials, or they can induce ROS DNA damage, and so on. So what I'm suggesting today is more investigations are required to really examine the potential benefits and possible effects of GBNs to be used for clinical use. You know, if we want to use the GBNs for clinical experiments, then we should consider the potential toxicity, genotoxicity, and carcinogenicity before using them to the clinic. And then if we want to use them for clinical translation, then we should work on the administration route, the optimal dosage that could provide the therapeutic benefits, and also the biodegradability of GBNs in the body. Okay, thank you very much for your listening. Then I would be happy to answer any questions if you have.
Thank you, Dr. Nafishe, for your presentation. Does anyone having any queries? Does anyone having any queries? As Dr. Irfan, do you have any queries? I hope there are no queries. Once again, thank you, Dr. Nashifa, for your
Yes,
presentation.
my pleasure. Thank you very much.
Thank you. Now let's move on to the next presentation. Is from Dr. Raymond Ucho from the Federal Polytechnic, Nigeria. Dr. Raymond, are you ready with the presentation? Please unmute yourself, Dr. Raymond.
Yeah.
Yeah, you're audible now. Now I'm making you as a presenter. Kindly click on the screen button to share your screen, please. Okay, Dr. Raymond, your presentation is with us. We'll be making you as we'll be displaying your presentation from our end. You can give your presentation by saying that. Please mention. Okay, we'll display your PowerPoint presentation from our end. Yeah, here is
Okay.
your
Yeah.
presentation. Please
Yes.
intimate to when you are willing to change slide with the command next, so that we'll be changing the slides. Okay.
Yes. Okay. Yeah. Yes. Okay. Yeah. This is Raymond Ozo from Federal Polytechnic Mobi. The title of my paper is Graphene, the Wonder Material of the 21st Century, Applications, Prospects, and Challenges. Can you hear me clearly? Can you hear me clearly? Hello? Hello?
Yes, we have changed the slide. We have
Can you
changed
hear
the
me?
slide. Please proceed.
Yes. So, graphene is a unique material of special interest with various mechanical, optical, thermal, electrical, and chemical properties. And that is why we call it a unique material. And I'm here to present with the following objectives to show us that graphene is an allotrope of carbon arranged in a hexagonal lattice and a nanostructure held by covalent carbon bonds. And graphene is a strong material, one carbon layer thick, and it has proved to be the thinnest material ever created. And also, 3 million graphene sheets can be stacked together to form a graphite and only give us a 1 millimeter thick material. It's very tough, it's flexible, it's a light material with high resistance, and it's happened to be 200 times more resistant than the steel. and 5 times lighter than aluminum metal. So it's very tough and also flexible and light. So I'm going to discuss the various means, slide 2, of preparing graphene, various ways of synthesis. Go to slide 2, please. So we're going to discuss the various procedures for synthesizing graphene. This is the summary of the abstract. This is the abstract summary. Next slide. Next slide, please. Next slide. Next slide. So this is the graphical illustration of a 2D material. You can see fullerene. It's a zero-dimensional fullerene, and they have a one-dimensional carbon nanotube followed by graphene. It's a single layer, atomic layer of a material, and then graphite, which is the source material to synthesize graphene. The next slide, please. Yeah, this is the various process of synthesizing graphene. We have two major approaches. We have a bottom-up approach and a top-down approach. Now, under the top-down approach, this is the system used by Adric James and Novos Level, the group that discovered this graphene in 2004, and they used the mechanical exfoliation or peeling of a graphite layer to extract graphene from a graphite. So I'm going to discuss just one from each group. I'm going to discuss mechanical exfoliation and then liquid phase exfoliation. And then under bottom up, I'll discuss chemical vapor deposition. So let me start with the bottom up approach, chemical vapor deposition. Now this is one of the most promising methods for synthesizing graphene cost effectively, and it can produce large area of graphene. So in this approach, a hydrocarbon, mostly methane gas, is injected into the reactor, which is a hot tube. And the hot tube of a nickel is the nickel metal is heated as a substrate, and then the methane gas is introduced, and the carbon decompose or degrade and deposit on the nickel slide. So nickel is the catalyst or a substrate. The carbon layer deposit on the nickel as a substrate, which can now be extracted by separating the different layers by either by dispersion, and they will separate the layers of a graphene, characterize them accordingly. So that is for chemical vapor. So it requires hydrocarbon gases. We normally use a methane under hydrogen atmosphere, and then to temperature about 900 degrees to 1000 degrees. The nickel catalyst is heated inside the hot tube, and then the gas is passed through, and then they are heated, and then the graphene layers deposit on the nickel metal, and they can be separated by mechanical force, and they are separated into the various layers. Now, I also discussed the chemical, mechanical exfoliation. The second method of graphene synthesis is a mechanical exfoliation, which is the process used by James and Novoselic in 2004. In this method, graphene is held by weak van der Waals forces. So when these forces are broken down by mechanical energy, they destroy the van der Waals forces, and it's a peeling process. The graphene layer are peeled and separated by dispersion by applying mechanical force from the graphite, and they are separated. But before this, there are other procedures that have to be followed. The first one is using a HOPG, that is a highly oriented biological graphite. The graphite is heated to up to about 500 degrees, and then it now subjected to mechanical pressure to disperse the layers from the graphite, and they are now baked and then separated. Go to the next slide and see the procedure. Next slide. You can see the approach now. The hydrocarbon gases are injected into the chamber, hot tube, at 900 degrees and above, and then the methane gas decomposes into carbon radicals and deposits on the nickel highly heated metal, and from there they are separated. And the other side is the bond gases are spat out, and the nickel catalyst is cooled down to almost to room temperature. As the temperature is being cooled down, the graphene sheet is being deposited on the nickel, and they are removed and separated. And the nickel is the graphene layer is started from the deposit on the nickel material. Next slide. Next slide. Yes. Then second procedure under top down is a mechanical exfoliation. As you can see on the slip, you see the graphite, and in between the graphite there are van der Waals forces holding the layers together. So this involves energy, mechanical energy used to disperse or separate the sheet from the graphite. But before then, it is highly heated to up to about 500 degrees. We call it highly oriented parotic graphite. In this process, the sheet thickness of 1 mm is used for dry etching by oxygen plasma to create a 5 micrometer deep mesas, and then they are baked and photoresist to be able to pull out the various layers from the graphite into the single graphite, as you can see on the right hand side. The right is the graphene layer, and the left is the graphite. Underneath is the van der Waals forces. So we apply energy, mechanical energy, to split or peel off the graphene layers from the graphite, as you can see from the diagram. Then next slide. Next slide. Next slide, please. This is the oxidation reduction of producing graphene. In this situation, the graphite is usually oxidized by oxidizing agents like a nitric oxide is normally used, and then after the oxidation, then the graphite is now reduced by normal reducing agent. So it oxidized to graphite oxide, and then after the oxidation, we introduce some other agent like potassium permanganate, as you can see, at 20 degrees centigrade, and the graphite is oxidized to graphite oxide. At temperature 98, we introduce water, aqueous water, and then we have graphite oxide, and then we should go further to apply more heat and introduce some additives, hydrogen peroxide and permanganate as assistants, and then the reaction is complete, and we have pure graphite oxide. Then we now introduce exfoliation to be able to, under vacuum, to kind of peel off the layers into graphene oxide. Then we use electrochemical series method to layer. So at this stage, at the baseline, you have graphene oxide. Then we use a normal reducing agent like a permanganate to reduce the graphite oxide into graphene layers. The next slide, please. The next slide. Yes. Then the last procedure there is the green chemistry, the one involving dead camphor leaves. This one does not require heating of any kind, but the dead leaves of the plant camphor leaves is the raw material. So we introduce the camphor leaves into the chamber, and they are burnt, or under pyrolysis, they are burnt to carbon particles, and then they are sonicated by sound system to separate the particles. And after separation, now they will now use a tyrosine compound, organic compound, a chloroform, D-triofane to separate the various layers of the graphene. So the triosine chemical help us to suspend or to separate the carbon material into graphene without difficulty. So by pipe interaction, the D-triofane help to separate the various layers of graphene after the pyrolysis, and then we arrive at the graphene layers easily. As you can see, the first stage, the second stage, and then the graphene comes up, and then with the help of the D-triosine in chloroform, then the graphene, for about 60 days, the graphene layers are separated without too much difficulty, and that will give us the graphene material. So we use dead leaves of camphor leaves, Cymonomum camphora, using a one-step pyrolysis under flowing nitrate atmosphere, and then heated to about 1 to 2 degrees at 10 minutes per minute. It is heated to without any external disturbances, and with the help of the alpha D interaction with the organic dye, D-triofane, the graphene layer can be dispersed or separated with the help of this chemical, D-triosine in chloroform solution. That is the green chemistry. Without using graphite, we use camphor leaves as a starting material to produce the graphene material. Next slide. Next slide. So when graphene is extracted, it can be also characterized to know whether it's crystalline, the diameter, the size length, and then the thickness of the layer. We normally use a term that is a traditional electron microscopy or scanning electron microscopy to be able to tell you the thickness of the layer, or is it crystalline, what's the morphology of the layer. This equipment, TEM and SEM, enable us to be able to size the thickness or diameter of the graphene material, and then we use SRD to show the crystal nature of the material. How crystalline is it? And they can be able to ascertain that this is a graphene material. The thickness must confirm, is it 1 layer, is it 2 layer, is it 3 layer, 7 layer? The SRD combined with the TM and SEM can give us this information, and we can be able to confirm that the material we produce or synthesize is a pure graphene. If it has impurities, UV spectrum can tell us impurities contained. That means the graphene is not pure. It has some impurities attached to it. So with this equipment and techniques, we can be able to detect the crystalline nature of the material, whether it is pure or not pure, whether it's crystalline or not, the diameter, the thickness, 1 layer thick or not. The combined equipment of this material can be able to give us an idea or estimate of the kind of material we just synthesized in the laboratory. So we use SRD, we use TEM, we use SEM to characterize that of crystal nature, morphology, thickness and diameter, and all the other properties associated with the graphene. Next slide. Next slide, please. Now, application and uses. Because of the unique property of graphene, having an optical property, electrical property, because of the band gap, graphene can conduct, because it has a free electrons at the interface. It has a free electrons, so they can easily migrate. So it has it conducts electricity. It has an optical property, electrical, chemical, and mechanical strength, flexible at the same time. So it can be used in lithium batteries, or either as a powder. So lithium batteries we use graphene as an electrode in lithium batteries because of the electrical property it possesses. And then it can be used as a capacitor because graphene-based material have been widely investigated to improve performance of small capacitors owing to their surface area. Graphene has a very wide surface area, and so that it can be used as a supercapacitor because of the mechanical and the electrical properties. And then other uses include as a sensor, it can influence property of, uh, of batteries. They also have a environmental application because of the thin nature of graphene. It can be used to absorb heavy metals and gases from the environment, either from the water or from the atmosphere, from polluted air environment. We can use the graphene to absorb gases like CO2, hydrogen gas, even methane gas from the atmosphere. So you can actually use to absorb these gases from the atmosphere and remove them or trap it because of the small natural size of graphene material. Also, in a water desalination procedure, you can desaline water through using a graphene material. Maybe water is very salty, you can pass them through graphene and they desalinize the water and remove some heavy metals and salts from the system. And water becomes pure and fit for drinking. So it's for water treatment also. Then in biomedicine too, it can serve as a thermal biosensor, biomolecule sensor, drug delivery, because it's selective. So it can allow some molecules to pass through, some are trapped. So those molecules that can pass through can be absorbed. And when they get to layer, it can be dropped by pH difference or temperature difference. Graphic can adjust and drop those molecules in the cancer cells without actually taking it everywhere. So it's very selective because of the pore size. It can absorb some gases or molecules in the system and then drop them at target organs where it is needed. So it can serve in drug delivery systems, but it has some effect because of the toxicity of a graft. It can pass some toxicity to the cells. So this area is still being investigated even now. Next slide. Next slide, please. Then, despite this use of graphene, it still have a toxicological effect that are yet to be confirmed. Though we know that it is toxic to cell system, but the exact amount has not been ascertained as to what quantity can influence toxicity. It is other being it's still being investigated, but as it is now, it has been used as a biosensor with little or no effect so far. But in pharmaceutical preparations, it is still being investigated. So, but for now, cannot conclude. It's still ongoing. Maybe in the next 1 or 2, 3 years, we can be able to decide this is the exact amount that can induce carcinogenic tendencies. But as for now, it has not been confirmed. And also, studies have proved that graphene physical chemical properties can also be used in various areas, and it can also have effects on the environment. Now, prospects, large-scale production of a graphene is ongoing. We can use chemical vapor deposition, liquid exfoliation, all these oxidation reduction methods can be scaled up. Mostly carbon vapor deposition can be scaled up and commercialized also. But currently in the market, we only have graphene films and powders in the market because these are the ones that can easily be produced by CDV, chemical vapor deposition, and then and the liquid exfoliation. So these two methods can be scaled up for industrial production, but the purity cannot be 100% confirmed. So the basic contain some impurities, and also the diameter can be affected. It may not give us a pure graphene at the moment. We can get up maybe 70% pure graphene from those industrial processes. So they are still being improved every now and then to get better ways of making graphene at industrial level. So with this ongoing research going on graphene and with the applications, it can still be improved in the future. But for now, the graphene films are available in the market and they are also very costly. But as the methods improve, the price may come down as we develop more methods of making them a commercial scale. And finally, the growth of the industry is still growing because it's not too popularly known. But with time, maybe the next 5, 10 years, we can increase the uses by creating more awareness how the graphene material can be used, either in the medical, lithium battery, environmental uses, and medical uses as well. Thank you very much. Next slide. So in conclusion, effort has been made to produce high quality graphene and their derivative from various methods, either top-down or bottom-up approaches, but they are very expensive at a commercial level. But it has been confirmed that carbon vapor deposition is scalable and is easy to produce at that scale compared to mechanical isolation or vapor arc production. So carbon vapor deposition and liquid extrusion are the best way to commercialize graphene production for now because of the cost of the mechanical isolation. It cannot be scaled up. So we use CVD and liquid exfoliation. So while they are still ongoing with the research to improve this method, we see face challenges on medical and environmental uses. But maybe in the next few years, we can have a breakthrough of discovering the exact amount in the body that can cause toxicity. But as for now, it has not been discovered the correct amount or quantity of graphene in the body that can induce cancer or being toxic. So for now, graphene frames and powders are available in the market, and they can still be used for the above mentioned uses I just mentioned. Next slide, some references. Next slide. This material were consulted, some of the references were consulted during the preparation. There's just few of them. I have more than 100, but there's just few of them that were displayed on the references. Thank you.
Thank you, Dr. Raymond, for your presence and presentation. Does anyone have any queries?
Yeah, my throat is dry. I'm having cough, so my voice is not sharp, but I believe
No worries,
you heard me.
Dr. Raymond. No issues.
Thank you.
I hope there are no queries. Once again, thank you for your presence and presentation, Dr. Raymond. Now let's
Thank
move
you.
on to the next presentation. Is from Dr. Momin Kweshime from the Hasimet University, Jordan. Hello, Dr. Momin. Are you ready with your presentation?
Yes, I
Hello,
am.
Dr. Momin. Yes. Okay. Now I'm making you as a presenter. Kindly click on the screen button to share your screen, please.
Okay.
Okay.
Okay, can you see my slides?
Yeah,
Yes,
your
you can
slide is
see.
visible. You can start your presentation now.
Thank you so much. Okay, this is Momin Kasaime. I am assistant professor in mechanical engineering from Hashemite University. Today I'm going to talk mainly about modeling, optimizing mechanical properties of FFF 3D printed thermoplastic parts. So let me first introduce myself. I am Momin Kasaimi. I'm working as assistant professor at Hashemite University. I have my PhD degree from University of Texas at Arlington. So part of this work that I want to present today have done there in University of Texas, UTA, and another part in the Hashemite University. Now let us talk a little bit about improving the mechanical properties of 3D printed parts. I'm talking about FDM or FFF printing technology, mainly for thermoplastic material. So if we'd like to improve the mechanical properties for this kind of materials, we can do it by process that is pre-printing, other process that is during printing, and other process can be done post-printing, like annealing. In my research, actually, we have focused on during printing technologies, maybe such as ultrasonic vibration, local heating, cold plasma treatment. We are in local heating and maybe rolling. I will explore more in the next slides. Okay, let us talk here about one of the research that I have done with my group in UTA, improved in print quality in fused filament fabrication through localized dispensing of hot air. So we have a hot air around the deposited filaments, which can be clear here in this slide, as you can see. So as you can see, while we are printing, we have installed hot air before and after printing, and then after this process have been done, we have examined the mechanical properties of the resulted parts, which has shown a significant increase in tensile stress, tensile strength, and some other mechanical properties, as you can see in this slide. This, so this was one part of my previous work. Now another part, it is about rolling. So it's almost for same purpose. We have integrated compression rolling while printing mechanism, as you can see in this slide. So it is a ball roller rolling. We already have three configurations, but the best one was a pre and post nozzle configuration, while we are rolling before and rolling after printing, so we can press or apply kind of pressure over the printed filaments while it's still hot and soft and can be deformed easily. So this one was really shows some significant improvement in mechanical properties. As you can see, the tensile strength is way higher than the baseline with no roller. Also, we have higher stiffness and some other mechanical properties. This motivates us to further investigate and trying to model the effect of this cytonozzle integrated compression and see how can this be improved or can be implemented in some other ways. So in this study, we have built a mathematical model. It is a physical based model. I will talk about it more. This model try to predict printed part thickness after printing and rolling, predict the part mesostructure after printing rolling, also trying to optimize printing rolling parameters, optimize filament to filament adhesion, as we will see. So this was my model. I have four cases, one for the first printed filament, contact between the steel ball and PLA filament while it's still soft and can be deformed easily. Then case two for two um, 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 filaments in contact, case three no rolling, and case four uh, um, um, for depositing filaments beside each other. And I have used the contact KJR contact theory, adhesion contact theory. So this theory about adhesive contact between two elastic solid materials. So I have assumed that the filament is elastic material, and between the two filaments we have adhesive contact in order to model the filaments mathematically by using this physics. The model has predicted the void diffraction, as you can see here the model. This is with no rolling, and this one with rolling, and I have compare it with the experiment, and it has a really good match between the model and the experiment. Now this is, as you can see, the errors was acceptable, were acceptable for predicting height, while we have uh, swell effect, and while we have no swell effect. This is swell just after the nozzle. Sometimes this will happen, and we can see also a good match with the experiment for reduction in filament height and void diffraction. Here another study is, we continue examining the effect of rolling on the fracture behavior. Okay, and then for baseline and between baseline and rolled parts. So this study objectives was to build a computational model along with a design and experiment to compare fracture behavior of rolled with baseline, study the fracture behavior of rolled part under different temperatures. For the computational model, we have tried to relate the filament half width, which is the contact width between the filaments, with the stress intensity factor, which has a great impact in fracture properties of the printed part. So after we have our first test, we can see that the rolled part under a 3-point fracture test, 3-point bending fracture test, shows us a very good improvement in fracture properties for rolled part if we compare it with the baseline. Also here we have compared it with 0.24 millimeter filament height. Why? Because this filament height matches the height of the filaments after rolling. So we can see how reducing the filament height without rolling in compare with the reducing of the filament height by rolling. As you can see, rolling give us way higher ultimate tensile strength and fracture properties. Also here we try to study the fracture by computational model by using ANSYS software. So we have built this model to represent the contact between two single filaments and see how this will affect the stress intensity factor, and how the contact width can increase or decrease the stress intensity factor, and moreover to see how this will affect the fracture properties. Now we can see here, this is the mesh for this model, and as you can see here, this is the mesh refinement study. The mesh should be selected critically in the areas where we have higher stress intensity and higher stress concentration factors. Now, as you can see here, our model, and here how it can expect the fracture happen while we have applying load in order to try to model the fracture behavior, as you can see here in this slide. And here we have tried to find the relation between the stress intensity factor and the contact half width. As you can see, as the contact half width increased, the stress intensity factor decreased, and this will improve the fracture properties of the printed parts. Here, moreover, we have one more study to study the effect of working temperatures on the fracture properties of rolled parts, because sometimes, as you know, we may use those printed parts at different working temperatures. So as you can see, 0 degrees C up to 45 degrees C, this is the mechanical behavior along with the fracture behavior of the 3D printed parts with rolling. Those was with rolling printing process. Now, as you can see here, also we try to understand the fracture from the fracture. We try to understand the fracture behavior from the fracture surface itself. So as the temperature decreases, the fracture become more brittle. As you can see, also as the temperature increase, the fracture become more ductile, and crazing effect can appear, as you can see in those parts. So now what we are working on, we are working on improving our mathematical model. So our mathematical model, as I have said before, it was two elastic solid materials in contact adhesively. Okay, now we need to further improve our model, as we know already from one of the research papers that have cited our research, that this was the only physical based model for rolling of thermoplastic material. So as I have known this fact, then I'm working now on improving our model and adding some more physics. As you know, the physics of solidification and maybe physics of viscoelastic effects of the material, and maybe the viscous depositing over a solid material, something like that, to improve our mathematical model. Also, in parallel, we are working on a computational model along with some experimental methods to further improve our process to give better mechanical and fracture behavior for our 3D printed parts for thermoplastic material FDM 3D printing technology. That's all at what I have. I try to make it as short as I can. So please, if anyone have any question, please let me know. Thank you.
Thank you, Dr. Momin, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Dr. Momin, for your presence and presentation.
Thank you so much.
Okay, now let's move on to the next presentation. Is from Dr. M.A. Fazal from Department of Mechanical and Metal Engineering, University of Jeddah, Saudi Arabia. Hello, Dr. Fazal. Are you ready with your presentation?
Yes, I'm ready.
Okay, now I'm making you as a
Please let me
presenter. Can you
share
click on the
the
screen
presentation
button to
slide.
share your screen, please?
Okay, sure.
Yeah, your screen is shared.
Okay,
Please.
please let me share the presentation slide. Uh, can you see my presentation slide?
Yes, you can start your presentation from the first slide.
Yeah, so the slide appeared, right?
Yeah, your slides are visible. You can start your presentation now.
Okay, thank you. President, Honorable Chairman, and my dear colleagues, Assalamu alaikum and good afternoon. Uh, Today I'm going to present a paper entitled Graphene-based materials for energy engineering and optoelectronic application. Let me introduce myself first. I'm Dr. Fazul. Currently, I'm working as an associate professor at the Department of Mechanical and Materials Engineering at University of Jeddah, Saudi Arabia. So here is my presentation outline. Actually, I'm going to talk about graphene, which is very hot topic nowadays. And first, I will highlight some properties of graphene, then application, then recent advances, upcoming progresses, and some limitation, and finally conclusion. So what is graphene? Graphene, we know that is a single layer of carbon atoms packed in hexagonal lattice. And mainly graphene is originated from actually graphite, means actually from graphite we can generate graphene, we can manufacture graphene by using different actually manufacturing technology. So here in this figure, we can see A is graphite, and that is transferred into graphene, which is two-dimensional material. Okay, so this graphene further can be actually folded or rolled into different dimension. For example, a graphene in figure C, we can see that is actually folded into actually 3D graphene. Means if we actually piled up some actually layers, then it could be 3D graphite. Okay, then it can be actually rolled in 1D carbon nanotubes. Okay, that is presented in D, and in figure E we can see it can be folded even zero actually dimension, that is fluorines. Okay, so we know that graphene is very special material, but why it is so special? uh, Graphene first was discovered by actually uh, James and Novolesso from Manchester University, and they won Nobel Prize in 2010. Okay, graphene has some properties in actually superlative degree, means it is thinnest material, it has highest conductivity, it is very strong material. So how thin is it? Graphene could be actually a million times thinner than a paper, and interlayer spacing is around 0.33 nanometer, and conductivity that is better than definitely copper, and uh, stronger. Graphene is stronger than actually this is the strongest material and is stronger than even diamond, and 200 times stronger than actually steel. Okay, so uh, how important it is? We know that graphene has some special characteristics. It has zero band gap energy and sp2 hybridization. Okay, and internal interlayer spacing that is very small, that is 0.335 nanometer level, and interlayer interatomic distance that is 1.42 angstrom. So because of these special characteristics, graphene has some outstanding properties, and those are electronic, thermal, mechanical, and optical. Okay, so because of these outstanding properties, graphene could be used in almost every industries, and in future we are expecting many new openings with this 2D material. So 2D, in addition to graphene, actually there are many 2D materials available in the market. So depending on the composition, 2D materials could be categorized into 5 different groups. So the first one is elemental, means graphene, ruthenium, uh, silicon. And non-metallic compound, we have graphene oxide, hexagonal boron nitride, and so on. Metallic compound, we have actually molybdenum sulfide, chromium chloride. Then we have salt type, okay, clays, calcium titanate. We have organic compound like polymer, metal organic framework, and so on. Okay, so since its discovery, 2D materials are widely used in nano devices, different types of nano devices. So, uh, but we should remember one thing, that due to electronic confinement and lack of interlayer interaction, the optical and electrical properties of these 2D material are entirely different from their base material or bulk material. For example, we can say graphene is manufactured from graphite. So graphite has one kind of property and graphene has totally different types of property. Okay, so uh, different actually property we get depending on the actually structure and composition. So we have a lot of 2D materials in the market, but among those, actually, graphene stands fast. Okay, on in advance actually in terms of some exceptional properties, as I just talked about it in previous slide. It has exceptional property, and those are electronic, optical, thermal properties, okay, and so on. So graphene, if we think about its derivatives, we have actually different types of derivatives of graphene, okay. For example, in this figure, we can see we have single layered graphene. So that is single atomic carbon packed in actually hexagonal lattice. Then two layer if compiled, okay, then piled up, then it will be bilayer graphene. Then we have few layered actually graphene. If few graphene layers are piled up, that will be few layered graphene. Then we have actually graphene quantum dot, then graphene oxide, we have reduced graphene oxide. So these derivatives have actually different types of properties, okay. So let's see the property property of graphene. First, actually, we actually check about electrical properties, okay. So the property, electric property, is generated from its actually electronic configuration. So we know that carbon has 6 atomic number, and that means it has 2 electrons in inner cell and 4 electrons in outer cell. And those 4 outer cell electrons are known as valence electrons. So these valence electrons are available for bonding, means one atom can bond with 4 different atoms. Okay, uh, but in graphene, there is exceptional case. What is that? That is actually 3 atoms, means each atom is connected with other 3 atoms, okay, and it will leave 1 electron free, and that is considered as pi electron, okay. The overlap and help in they overlap and help in carbon-carbon actually bond formation in graphene, and electrons can move freely in pi orbitals, okay. That's the mechanism for having high actually mobility in the graphene, high electron mobility in the graphene. So graphene has extremely high electrical current density, okay, millions times better than that of copper. It has actually extremely high electron mobility. Then graphene has low resistivity, okay. Then it can be turned, it can be actually modified into semiconductor material by doping some band gap materials, okay. We know that graphene actually has no actually band gap energy, okay. So if some other materials are doped, then its conductivity can be changed, okay. It can carry electricity with 100% efficiency, and this actually superior electrical property has made it suitable for different electronic devices. And we have different types of devices in market based on graphene, bioelectric sensor, PV cell, ultrafiltration, water ultrafiltration, then optical electronic properties, optical actually devices at where graphene is used, and energy storage system where graphene is used. So in addition to electric properties, there are some other properties which are exceptional, like optical properties. Graphene has around 97.7% actually transmission of light, okay. So because of this extraordinary property, it can be used in LCD and LED devices. Mechanical properties, if we think about, it is stronger than diamond, okay, 200 times greater, actually stronger, means stronger than steel. So actually another property is combined with this strongness, that is flexibility, okay. Then thermal conductivity, it has very high thermal conductivity. And the last which is very important property, that is surface area of graphene is very actually large, and because of that actually it can be used to monitor glucose level, hemoglobin level, cholesterol level, and DNA sequencing through sensor. So we have actually seen different types of derivatives of the graphene, and those derivatives have different actually level of properties. For example, if we think about surface area, single layered actually graphene that has actually the largest surface area, but whenever we make it bilayer or few layers, then surface area is reduced. Okay, that means actually the single layered one, that is the best in terms of actually surface area, optical transparency, then electron mobility, thermal conductivity even. But the last two mechanical properties, ions modulus and tensile strength, for single layer that is comparatively less compared to bilayer and few layered actually graphene derivatives. Okay, so for these so we can understand that graphene and its derivatives have actually very good electrical, mechanical, optical properties. Okay, and because of that actually these are applied in different application. For example, in supercapacitor, in biological device, then composite, catalyst, ultra filtration, energy, electronics, sensor, and so on. Okay, so application of graphene, because of combination of these properties, we can see here strength, zero band gap energy, ultra high carrier mobility. Okay, the graphene is considered as a very new and attractive material. Okay, for different devices like touch screen, sensor, solar system. Okay, so some actually applications of graphene we can see here. For example, biological sensing devices. Due to having large surface area and high conductivity, um, graphene could be used in sensor, and that sensor could be different types. Okay, it could be actually nanopore sensor or optical sensor or electronic sensor. These graphene based sensor could be used to actually level hemoglobin, to monitor the hemoglobin level or cholesterol level, or even for DNA sequencing. Then photovoltaic cell, we know that currently in the market PV systems are mainly actually made of silicon, and silicon could be either um, monocrystalline or polycrystalline. This silicon uh, is good for actually PV solar system, but has very low efficiency, conversion efficiency, energy conversion efficiency. It is around 25% in the field. Okay, and maximum actually theoretical efficiency for silicon actually based PV system is around 29%. Okay, so with that efficiency we are not happy. In that case we have to seek for other important materials. In that case graphene could be a very actually interesting material to increase the efficiency. Not only increasing efficiency, it can actually give another interesting property, that is flexibility. Okay, because graphene is a strong material, at the same time it is flexible material. So graphene in future actually we are expecting in market a graphene based actually solar system. Okay, and another advantage we have for this photovoltaic solar system, graphene based photovoltaic solar system, it can actually work with all wavelengths, but this actually is not actually applicable for the current material silicon based PV solar system. Okay, so a lot of opportunities actually we have to explore actually with the help of graphene. Okay, especially in photovoltaic solar system. Now, optoelectronic devices, graphene could be the most actually useful material for optoelectronic devices, because it can transmit around 97.7% of the light. Okay, which is very important for optoelectronic devices. Okay, especially touch screen based actually devices. Then graphene also could be used as a composite material or even nanofluids. Okay, for example, in the picture we can see cyclic helmet. It can be made of graphene, and it can actually also be used to dispense the heat, okay, more efficiently in the cooler systems. Then graphene also could be used for ultrafiltration system. We know that graphene has very small pore diameter, and through which actually water molecule can pass, but other actually gas or liquid molecules cannot pass. So uh, graphene actually could be used for filtration process very efficiently. Then in case of energy storage system, actually graphene has wide application because if you see, especially in the energy storage system like battery, in the market we have different types of battery, and those batteries actually have some limitation. For example, short circuit problem or overheating. Okay, but if we use graphene, then we can introduce some special actually properties. For example, elasticity, surface area, porosity, conductivity, electrochemistry. So with the help of these properties, actually the capacity or performance or charging actually time, uh, or actually efficiency of the battery, we can drastically improve. Okay, so in the market, lithium battery is most popular, but it has some problem. For example, electronic short circuit or overheating, and that can be easily solved by with the use of actually graphene. So recent advances with graphene. Graphene, we know that it doesn't have any band gap energy. Okay, so but it is that's why actually it doesn't have band gap energy. That's why its electrical and thermal conductivity is too high, and that is very important for electronic devices. But there is a limitation actually. For electronic properties, turn-off property is very actually important. So as there is no band gap energy, so turn-off property cannot be achieved. So opening of band gap has already been developed over years. So this was the problem of opening band gap in graphene, but that is solved. But still, it is costly process. So in future, we are expecting actually to make it actually cheaper. Then use of graphene and recent advancement. Graphene is used in touch screen displays, okay, for getting uh, super thin, bendable, and higher efficiency. Okay, graphene-based transistor can ensure faster processor. Then batteries, graphene-based batteries actually hold longer charge and take less time to charge. Okay, then we can produce actually graphene based robust rackets. Okay, then water filtration also we can do efficiently with the help of actually graphene based materials. So upcoming progresses, actually super thin and faster reacting actually graphene flat screens are to replace the current actually LCDs and LEDs. Okay, and also the property of graphene's transparency is used to improve the LEDs and other solar system. Okay, and already mobile companies like Samsung and Nokia, they have taken the graphene technology and decided to blend it with the upgrading of its function, performance, and looking features, okay, of the mobile. Okay, so the next generation smartphones are expected to be flexible touch screens. Okay, and these are already actually developed, but not at bigger scale, not available in the market at bigger scale. But in future, uh, this kind of actually technology is coming, and in that case graphene actually is working at the root of the technology, and it is actually it make it flexible, uh, actually touch screen, then resizable and foldable body, and large battery backup, longer life, auto charging with extraordinary features. So graphene has still some limitation. Actually, people are working, scientists are working with graphene throughout the whole world. Okay, and major limitations are listed here. Graphene has weak bonding between interlayers, means layer to layer. Actually, bonding is very weak. In some cases, graphene aided devices are not stable. Okay, stability is very less. Okay, single seed graphene is hard to produce, so we have to develop actually a better manufacturing actually process to reduce the cost and to ease the system production system. Then when graphene can be considered a semiconductor like silicon, it lacks one crucial property, and that is the switching off. Okay, and for that, for solving this problem, we have to actually open band gap uh, in the graphene material. Okay, and that is already done, but this process is very costly. In future, uh, actually cheaper process we are expecting, that new fabrication and manufacturing methods actually have to be evolved for normal use in electronics, for normal use of graphene in electronics. So at the end, actually we have conclusion. So we have seen that graphene has some special characteristics. For example, speed to height reduction, then interlayer spacing is very small, that is 0.335, and interatomic spacing, that is 1.42 actually angstrom. Then it has 5 orbitals and 0 band gap energy. All these characteristics contribute to have extraordinary actually properties, like we have extraordinary mechanical properties, electrical properties, and optical properties. So because of these extraordinary properties, graphene is suitable for different actually electronic and optoelectronic devices. Okay, and although graphene has not touched our commercial lives at bigger scale yet, it has great potential and will eventually reach to us very soon. Okay, whether or not graphene replace silicon as a material of energy generation or transfer, it will help engineers greatly in advancing the technology and opening new innovations. So here are some actually references. That's all. Okay, thank you everybody, and I highly appreciate to the organizer for arranging this, for giving me opportunity to present my paper. Thank you everybody.
Thank you, Dr. Faiza, for your presence and presentation. Does anyone having any more queries? I hope there are no queries. Once again, thank you, Dr. Faiza, for your presence and presentation. Now, let's move on to the next presentation. Is from
Thank you.
Dr. Vijay. Thank you. Now, let's move on to the next presentation. Is from Dr. Vijay from Nagaland Central University, India. Hello, Dr. Vijay. Are you ready with your presentation?
Yes, ma'am. Yes, I'm ready
Okay,
with the
and now I'm
presentation.
making you as a presenter. Kindly click on
Okay,
screen button to share your screen, please.
okay. So, is it visible?
Yeah, your screen is visible now. Can please make it in the presentation mode and start your presentation now. Thank you.
Okay, okay. Thank you, organizers, for giving me the opportunity to present the papers here. So, myself, Dr. Vijay, I am assistant professor in Department of Physics, Nagaland Central University, India. So today I am going to present a paper on fabrication of a flexible supercapacitor using the polypyrrole nanotube composites. So mainly my presentation contains uh, fabrication of solid state supercapacitor using CSPNT nickel oxide core shell nanostructures and MOS2 quantum dot incorporated with the chitosan, which will be embedded on the polypyrrole nanotube for the supercapacitor applications. So first of all, the supercapacitor, it's an energy storage device. So it's also called as an ultracapacitor or a electrochemical capacitors. So this supercapacitor will bridge the gap between the conventional capacitors and the rechargeable batteries. So the energy storage in supercapacitors arises from the electrical double layer as well as the reversible redox reactions at the electrode and the electrolyte interfaces. So supercapacitors usually have a higher magnitude of capacitance than the conventional capacitors, and they are characterized by the high power densities and the energy densities. And they also have a fast charge discharge process and also the cyclic stabilities. So in order to understand the supercapacitors, we have to understand this Ragon plot. So where the Ragon plot will give the comparisons of various energy storage devices. So here supercapacitor will make a bridge between the normal capacitors and the batteries. So so if you see the capacitors, normal capacitors, which have a higher power densities, whereas it has a very lower energy densities. In case of batteries, we have a higher energy densities, but we have a very low energy density, power densities. So these supercapacitors will make a bridge between the conventional capacitors and the batteries. So this supercapacitor will offers high energy density as well as the power density without compromising the power densities. So the classification of the supercapacitors. So based on the um, charge storage mechanism, the supercapacitors are classified into three categories. One is electrical double layer capacitors, then the pseudo capacitors, and the hybrid capacitors. So for the electrical double layer capacitors, usually the carbon materials are used, and in case of pseudo capacitors, the conducting polymers or the metal oxides are used. So in case of a hybrid capacitors, usually the composite hybrids or the symmetric hybrids or the battery type hybrid materials are used. So here we are focusing on the nanostructured conducting polymer composites. So these nanostructured conducting polymer nanocomposites will have some of the important features where it has a large fraction of surface is exposed to the reactions and high surface area compared to the volume and the spatial confinement, and it also reduces the number of imperfections that do not exhibit in the corresponding bulk materials. So these are some of the important features of nanostructured conducting polymer compared with the conducting polymers. So here we also used metal oxides and 2D materials. So the metal oxides are one of the electrode materials involving the redox capacitance, so imparting from the high specific capacitance. And the commonly used transition metal oxides in the supercapacitors are the ruthenium oxide, iridium oxide, manganese oxide, and the cobalt oxides. And these supercapacitors exhibits specific capacitance values range from 50 to 1100 farad per gram. So 2D materials also show a double layer charge storage capacity, and which provides excellent supercapacitors properties due to the large surface area. Among the 2D materials, MOS2 exhibits a high specific capacitance and the cyclic stabilities. So our aim and objective of this proposed work is to investigate the properties of the nanostructured conducting polymer material for the supercapacitor applications. So here we have incorporated metal oxides and the quantum dot materials into the nanostructured conducting polymers. So in the first part of our studies, we have incorporated the nickel oxide into the polypyrrole nanotube, and in the second part we have incorporated MOS2 quantum dots into the polypyrrole nanotube. So then what we have did is we have fabricated the supercapacitors. So all solid state symmetric supercapacitor we have fabricated using these materials. So these are the materials which is used for synthesis of CSPNT nickel oxide nanocomposites and the CSPNT MOS2 nanocomposites. So here, for the fabrication of the electrodes for the supercapacitors, we have used 80% of the prepared samples, then 10% of the activated carbon, and 10% of the PVDF. So here PVDF will be act as a binder for the to coat the material into the electrode. So this PVDF will act as a binder. So then these materials will be dissolved into the NMP solutions. So then this will make a slurry. This slurry is coated onto the stainless steel electrode. So here we have analyzed this supercapacitor studies in a three electrode system as well as a two electrode system. So in the three electrode system, so the fabricated electrodes will work as a working electrode, and AgAgCl is working as a reference electrode, and platinum wire will work as a counter electrode. So in case of fabricated all solid state symmetric supercapacitors, so here if we use the same materials for the anode and the cathode, then it will be a symmetric supercapacitors. In case of a asymmetric supercapacitor, we have used the activated carbon as a cathode and the prepared samples as a anode. So this will make a asymmetric supercapacitors. So in order to calculate the specific capacitance, we have used these formulas. Um, and in order to calculate the energy densities, we have used these two formulas. So we have carried out various characterizations in order to study the properties of the materials. So we have carried out XCRD, XPS, so then to study the structural property, then FSM and HRTM is used to study the morphological studies, and the electrochemical studies were being carried out using the CHI 66E electrochemical workstations. So in the first part of our studies, we have fabricated all solid state symmetric supercapacitor using CSPNT nickel oxide core shell nanostructure. So here, what we have did is uh, we have fabricated the self-degradable template using the methyl orange and the ferric chloride. So this will make a template. So when this template is formed, then we have added a polypyrrole. So pyrrole we have added, then we have kept it for polymerization, then it will become a polypyrrole. So then after that, so we have used the nickel oxide precursors and we have kept it in a hydrothermal. So that will form a PNT nickel oxide nanocomposites. So this nanocomposite, whatever we have prepared, we have characterized using X-ray diffractions. So in this X-ray studies, here in this X-ray studies, we can clearly see that the nickel oxide PNT shows all the peaks or all the characteristics peaks, which is at 37.15 degree and 43.30, 62.77 and 75.19. All these peaks are belongs to the nickel oxides, which is indexed to 111 plane and 200 plane, 220, 311 and 222 diffraction planes respectively. And these results were being compared with the JCPDS file also, which is matching well with the JCPDS file. And here we can see two major characteristics peaks of chitosanes, that is at 11.70 and 21.77, which is normally broader and less intense, which is belongs to the chitosan peaks. Then we have carried out XPS studies. Here we can confirm the all the elements which is present in the prepared samples, the carbon, nickel, then the nitrogen and oxygen. So this confirms our synthesis. Then we have resolved this XPS spectra into the high resolution spectra. So here oxygen spectra at a binding energy of 531.1 and 532.2 and 533.6 electron volts are ascribed to the oxygen species in the nickel oxide and water molecules in the material structure and the polymer oxidized bonds. So the high resolution spectra of nickel 2p shows two main characteristics peaks, that is at 854 and 872.5 electron volts, which is corresponding to nickel 2p 1 by 2 and nickel 2p 3 by 2 respectively. So the difference between this binding energy between 2p 1 by 2 and 2p 3 by 2 is 18.5 electron volt. So then we have studied the morphological studies using FSM and HRTM characteristics. So this FSM studies shows that the PNT composite, the polypyrrole nanotube is uniformly dispersed, and which is having a smooth surface with an average diameter of 80 nanometer, and the length of this polypyrrole nanotube is of the order 3 to 5 micrometers. The nickel oxide nanoparticles with the average diameter of 50 nanometers is homogeneously and densely attached onto this polypyrrole nanotube. Then we have carried out the HR-time analysis. So the HR-time analysis clearly witnessed that the PNT will be the core material, whereas the nickel oxide is attached onto this core shell. This nickel oxide will act as a shell material, which is attached to the PNT polypyrrole nanotube. So the HR-time analysis further confirms that the PNT is a one-dimensional hollow nanotube with an average inner and outer diameter of 80 nanometer and 100 nanometer respectively. So these are the elemental mapping images of the prepared samples. So here we can see the different elements present in the prepared samples, which is again confirms the synthesis process. So here we can clearly see the carbon, the amount of carbon, nitrogen, oxygen, and the nickel, which is distributed in the prepared samples. So then we have carried out electrochemical characterization in order to study the electrochemical properties of prepared samples. And we have carried out these electrochemical studies in a 2 electrode system as well as a 3 electrode system. So these are the images which is shown here are 3 electrode system, the cyclic voltammetry and the GCD studies, the galvanostatic charging discharging studies. So here in the cyclic voltammetry studies for the different samples, a pair of distinct redox peaks was detected, which shows that all the nanocomposites possess a typical pseudo capacitance properties. So then what we have did is we have took CSPNT nickel oxide, which shows a high capacitance, and we have carried out for a different current densities. Okay, but for a different scan rates. So here the CV curve retains an identical shape without any distortion. So the peak current increases implies that the volumetric current is directly proportional to the scan rate. So in the galvanostatic charging discharging, all the for all the samples, which exhibits asymmetric triangular shape, which indicates that again, which confirms the pseudocapacitance properties, which is reliable with the CV studies. So here we have calculated the specific capacitance for the each of the samples. The nickel oxide CSPNT exhibits the highest specific capacitance of 934 farad per gram, which is higher than the other two samples, nickel oxide PNT and the pure PNT, which is at a current density of 1 amperes per gram. So then in order to study the solution resistance and the charge transfer resistance, we have carried out electrochemical impedance studies for different samples. So here we have found the solutions resistance for nickel oxide CSPNTA of 0.87 ohm, which is very less than compared with the other samples, and the charge transfer resistance is about 1.01, which is less than compared to the other samples. The low frequency region of the Nyquist plot is a vertical line which exhibits the characteristics of an ideal electrode material. So then we have carried out electrochemical studies for nickel oxide CSPNT for the symmetric supercapacitor devices. So here also we have carried out cyclic voltammetry and the GCD studies. So in the cyclic voltammetry studies, which shows a quasi-rectangular shape with the small redox peaks, which clearly indicates that the Faradic type behavior of a solid-state symmetric supercapacitors. And in the GCD studies, it shows a asymmetric triangular shape, which is indicating the pseudocapacitance properties. The discharge time get increased with the increase in the current density, which is due to the limitation of charge transport diffusion coefficient at a higher current densities. Then it shows that the lower electrochemical solution resistance values of 0.85 ohm indicating a low series resistance, And the charge transfer resistance of a symmetric supercapacitor is found to be 1.01 ohm. So at the low frequency region, the Nyquist plot shows a vertical line, which is an ideal supercapacitor behavior. And we have tabulated all the specific capacitance values for different scan rates and different current densities. So here at at a current density of 1 A by G, it shows a specific capacitance of 453 farad per gram, and the corresponding energy density and power densities are 69.39 and 505.72. So here, the cyclic stability studies are also carried out. So the symmetric supercapacitor shows an excellent cyclic stability with an 84.91% capacitance retention was observed for 1,000 cycles at current density of 10 A by G. And the symmetric supercapacitor device exhibits a maximum energy density of 69.39 at a power density of 505.72, which is higher compared to all the reported result. And these results were being published in the Electrochemical Acta. And in the second part of our studies, we have synthesized MOS2 quantum dot, and we have embedded this MOS2 quantum dot onto the polypyrrole nanotube for all solid state supercapacitors. Here also we have followed the same process. We have fabricated the self-degradable template using a methyl orange and the ferric chloride. Then we have added pyrrole monomer, and then we have kept it for a polymerization. Then we have added a MOS2 precursors, and we have carried out using hydrothermal methods, and this CSP NT-MOS2 is formed. And here the X-ray diffraction studies also carried out. So in this X-ray diffraction studies, we can see that there is a broad band peak located at 2 theta 20 to 30 degree, which was attributed to the existence of amorphous polypyrrole nanotube. And surprisingly, we have here we haven't identified any diffraction peak corresponding to the MOS2 quantum dot in the PNT MOS2 and CSPNT MOS2 nanocomposite, because of the ultra small size and the low content and the high dispersion of MOS2 quantum dot, which was confirmed using HRTM analysis also. And the the chitosan exhibits two peaks at 10.48 degree and 20.95 degree, which is typically a fingerprint peak of chitosan. The CSPNT MOS2 shows a distinct peak attributed to the overlapping of broad nature due to the presence of chitosan and the polypyrrole matrix. So the XPS studies also shows the presence of all the elements which is present in the prepared samples. Here we can see the molybdenum and sulfur peaks along with the carbon, nitrogen and the oxygens, which again confirms the synthesis. And we have resolved this XPS survey scan spectra into high resolution spectra. So here the molybdenum 3D spectra shows two obvious peaks at 229.2 and 232.4 electron volt, which is belongs to the molybdenum 3D 5 by 2 and the molybdenum 3D 3 by 2, which is consistent with the MO4 plus in MOS2. And the small peak at 225.9 electron volt is assigned to sulfur 2s of MOS2. The two peaks located at 161.42 and 163.5 electron volt are attributed to the sulfur 2p 3 by 2 and sulfur 2p 1 by 2 components. So in order to study the morphological studies, we have carried out field emission scanning electron microscope studies. So here the polypyrrole nanotube shows uniform halo nanotube like structure with an average outer diameter of 80 nanometer and the length of 1 to 3 micrometer. So the outer diameter of CSPNT MOS2 tubular nanostructure, tubular structured nanocomposite is in the range of 100 to 200 nanometer, which has clearly increased due to the growth of MOS2 quantum dot on the PNT polypyrrole nanotube surface. So the high resolution HRTM analysis, here it is evidently observed that the polypyrrole nanotube as a core material is tightly bound and covered by the MOS2 quantum dot to form a core shell nanostructure. The morphology of Chitosan polypyrrole nanotube embedded with the MOS2 shows sufficient porosity that enables more feasible diffusion of electrolyte, and also the surface of CS PNT MOS2 nanocomposites is rougher than that of the PNT MOS2 nanocomposites. The enlarged image of MOS2 quantum dots present here, sorry, present in the PNT MOS2 nanocomposites shows ordered lattice fringes corresponding to 110 plane of MOS2 with the crystal spacing of about 0.488 nanometer. So these are the elemental mapping images. So here we can see the distribution of different elements. Here we can see the molybdenum and as well as the sulfur, how it is distributed among the polypyrrole nanotube. So then we have carried out electrochemical studies using a 3-electrode system. So here for the different samples we have carried out CV studies, and then for CSPNT MOS2 we have carried out cyclic voltammetry studies for different scattering rate. So the increase in the integrated area of the CV loops inferred a much higher capacitance for CS PNT MOS2 nanocomposites than the PNT MOS2 and pure PNT. The CV, the cyclic voltammetry studies of CS PNT MOS2 for different scan rate shows a highly symmetric quasi-rectangular shape, indicating that MOS2 possesses good electrical double layer capacitor characteristics. The specific capacitance obtained from the CV studies is about 833 and 584 and 386 farad per gram for CSPNT MOS2, PNT MOS2 and PNT, the pure PNT respectively. The specific capacitance obtained from the galvanostatic charging discharging studies are found to be 793, 395 and 209 farad per gram for CSPNT MOS2, PNT MOS2 and the polypyrrole nanotube respectively. So here we can clearly, the result clearly shows that the CSPNT MOS2 is a feasible material for the supercapacitor studies. So then we have carried out electrochemical studies for different samples, and we have found that the solution resistance of 0.36 for CSPNT MOS2. And again here in the low frequency region, the Nyquist plot shows a vertical line, which is an ideal characteristics for the supercapacitor studies. Then we have carried out, we have fabricated the symmetric supercapacitor using CSPNT MOS2 nanocomposites, and we have carried out different characterization techniques such as cyclic voltammetry and galvanostatic charging discharging studies. So all the cyclic voltammetry curve exhibits a pair of typical redox peaks corresponding to the Faradic redox behavior. The galvanostatic charging discharging curve shows nearly a symmetric triangular shape, indicating the pseudocapacitance behavior. The discharge time gets increased with the increase in the current density, and the longer discharge time will give rise to a larger capacitance that we can see here from the graph. It also shows the lower electrochemical series resistance of the order of 0.81 ohm, which indicates the lower series resistance, and the charge transfer resistance of 0.95 ohm. And again at the lower frequency region, we can see a vertical line which indicates the ideal supercapacitor behavior. So then we have calculated the energy densities and power densities for different samples. So here our work, in our work, it shows that the energy densities of 32.12 at a power densities of 7,680, and the capacitance retention of 91.2%, and the Coulombic efficiency of 98.5%. So these are the devices which we have fabricated in our lab. So then we have carried out a series of mechanical flexibility studies in order to perform and validate the potential application for the portable and the wearable electronic devices. So here we have here in the CV, in the cyclic voltammetry studies, there was no significant difference was found among the cyclic voltammetry curves. Almost overlapped cyclic voltammetry curves were achieved with the various bending positions at a scan rate of 50 millivolt per second, which emphasizes the outstanding flexibility and stability of a fabricated symmetric supercapacitor studies. So in the conclusion, we have synthesized the coastal nanostructure using nickel oxide CSPNT nanocomposites and CSPNT MOS2 nanocomposites for highly efficient all solid state symmetric supercapacitors. The nickel oxide CSPNT coastal nanostructure exhibits significantly high specific capacitance of 934 farad per gram, which is much higher than the nickel oxide PNT and the pure PNT at a current density of 1 A by G, which is measured using a 3 electrode system. Then the fabricated all solid state supercapacitors also shows the high specific capacitance of 453.21 farad per gram at current density of 1 A by G, and the energy density of 69.39 at a power density of 505.72. Further, it shows an outstanding cyclic stability of a fabricated symmetric supercapacitor device with the capacitance retention of 84.1% even after the 10,000 cycles at a current density of 10 A by G, the amperes per gram. So the fabricated chitosan embedded with the polypyrrole nanotube MOS2 coastal nanostructure, which exhibits high specific capacitance of 793 farad per gram using a 3 electrode system, and all solid states, the fabricated all solid state symmetric supercapacitors shows a capacitance of 392 farad per gram at a current density of 1 A by G, and the energy density is found to be 32.12 at a power density of 7,680. So this performance makes CSPNT MOS2 coastal nanostructure as a favorable electrode material for supercapacitor studies. So currently we are working on supercapacitor studies by changing the various electrolytes like ionic electrolytes and all. So then the influence of arrangement of layers in the multi-layered electrodes on the supercapacitor studies are also going on, and the flexibility supercapacitor studies, we are working on those studies now. So these are the publications which is published from our group. So, and I would like to thank Professor Devendra Payach, Bangalore University, for his guidance, and I also thank our funding agencies, DST, the Department of Science and Technology, Government of India, and Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore, and one of my collaborator, Dr. Raghavendra Bairi, the Associate Professor, NM AIT, Nitte Karkala in Karnataka. So thank you.
Thank you, Dr. Vijay, for your presence and presentation. Does anyone having any queries?
Thank you, ma'am.
I hope there are no queries. Once again, thank you for your presence and presentation. Now let's move on to the next presentation. It's from Dr.
Thank you.
Amna Mazen from University of Detroit, Mercy, USA. Hello, Dr. Amna Masan. Are you ready with your presentation?
Hi, yes, I'm ready. Can you open
Okay,
the
now
share,
I'm
please?
making you as a presenter. Kindly click on the screen button to share your screen, please.
Mhm. Can you see my?
Yeah, your screen is shared. Please make it in a presentation mode and start your presentation now.
Okay, thank you. Hello, everyone. I am Amna Mazen. I'm PhD student and teaching assistant at University of Detroit Mercy. Today, will present my work on factors affecting the tensile strength and impact toughness of 3D printed parts using some of the DOE experiments, which is fractional factorial design. So basically here in this presentation, first I will say some introduction about our work. Then I will discuss the methodology that we used in this work. Then we will make some data analysis and do verification experiments to confirm the results that we got in the main experiment. And finally, we will make a conclusion about the main findings in this work. So basically here we are talking about fused filament fabrication, which is basically an adaptive manufacturing technique that we build some 3D part using layer by layer. So it is very useful in many fields like aerospace, like food industry, and all of this stuff. First, we have the commercial 3D printers that wasn't open source and it was used for many years. So we have for the commercial 3D printers, we have enough work that explain in detail the tensile strength and impact toughness and all of the mechanical properties of these printers. But in the last decade, we also have the open source printers, 3D printers, which is very cheap, less than $1,000. So many people, many home users bought these printers and start use them at home. But basically, we don't have enough information about the properties of these 3D open source printers like Prusa, like RepRap, and all of these printers. So basically, this is why we did our work. We have at University of Detroit Mercy one of the open source printers, which is Prusa, and we don't know the like specific information about the tensile strength and the impact toughness of the parts printed by this printer. So we did some experiment to get information about this. So as I said, we in this work we will study tensile strength and impact toughness, which are very well known tests to get information about the mechanical properties of the 3D part. So basically, tensile strength is basically we got a 3D printed sample. Then we apply some tensile or tension up to break. And on the other hand, the toughness is basically we like hit the part up to break, and we record how many energy stored in this part. So what was our plan? Well, our plan was to use Prusa i3 MK3S, which is a printer that we have at university, and we will make some of the DOE experiments, which is a fractional, half fractional factorial, to study the effect of some factors. The factors that we choose in this study are the print orientation, layer height, extrusion width, nozzle diameter, and the filament temperature. So we have 5 factors. For every factor, we have 2 levels, low and high. So basically, this will get us 32 experiment. But we use the half fractional factorial, so it will be only half of them. So we only implemented 16 experiment to determine the first which of these factors really affect the tensile strength and impact toughness, and for those that affect, what is the optimum choice for them, so we get the maximum of the tensile strength and the maximum for the toughness. So to implement this experiment, we designed some sample by using SolidWorks. So we need to do two experiment, one for the tensile test. So we make a part in the sample that have a smaller cross section. So this is where when we apply a tension, this is where the fracture will happen. And we also make a notch, so we will apply we will use it when we apply the impact toughness test. And as I said, we use 5 factors. We like examine the effect of 5 factors, which is first the print orientation. We use either it will be the parts will be printed horizontally, like how the layers stick to each other horizontally or vertically. And the layer height we used 0.15 millimeter or 0.25 millimeter. And the extrusion, which we make it as a percentage of the nozzle diameter. So it is either 100% of the nozzle diameter or 150% of the nozzle diameter. And the nozzle diameter we use two options, either zero point 0.4 or zero point 0.6. And finally, the filament temperature. This one depends on the material that we use. With the one that we used gray PLA. And according to the data sheet, it can afford temperature between 208 and 217. So this is the low and high levels of temperature. So to implement this experiment, we need some physical or hardware, and we need some software. For the hardware, we need a 3D printer, which is Prusa we have at the university, and we need some material, which is the gray PLA that we used. Then we need some hardware testers to implement the azote impact test, and we need also some hardware to implement the tensile strength. And also we need something to measure the actual diameters, like the cross section of the part where we have the fracture. So we need calipers for this. This is the hardware that we used, or the physical elements that we used. In addition to the hardware, we also used some software to implement the analysis of the data, which is Minitab. And as I said, all these machines was provided by my University of Detroit Mercy. So this is the printer that we used in our experiment, which is Prusa i3MK3X. And this is the tester that we use for the impact toughness. Basically, we fix the part here at the notch and then let this hand free, so it will hit it and break it, and we measure how much energy was absorbed in this part. And basically here, this is a tester we used for the tensile strength. We apply tension. Here is the part we fix it here. And then we apply tension up to 20 kilonewton, up to we having the fracture happen, and we measure the tensile strength. So after we implement the experiment on the 16 parts that we printed, we took this data and start to make analysis by using Minitab by investigating the effect of every one of them. So basically, as I said, we make a fractional factorial experiment, not full factorial. If we are implementing full factorial experiment, it will be we need a 32 experiment, which is 5 to the power 2. But in our case, we made only half of them. But it is not like there is a rules to choose the half of them, which are this there should be a balance and independency between the factors, which means we have for every level we have low level and high level. There should be balance between number of low level and high level. So here we have 16 experiments, so we expected to have 8 of low level and 8 of high level of every factor. And also we expected to have independence between factors, which means if we make dot product between any of the two factors, it should be equal to 0. And this is actually the experiment, the results of the experiments that we did. We used it as input for the Minitab. And this is a part is after we applied the two tests, the tensile strength and the impact toughness. And here let's have a look on what we got after we have a look on the data that we have. We notice that for the NBB, for the impact toughness, that only A, which is the first factor, which is the print or orientation, that is affected, is the only one that is significant. This is the only significant factor for the impact toughness. This means that regardless of whatever the other four, the level of the other four factors, it doesn't matter for the impact toughness value, only the print orientation, whether it is horizontal or vertical, is really affects the value of the impact toughness. And also by using Minitab, we were able to get an equation to calculate what is the impact toughness given the print orientation, which here we have two levels, so -1 and 1. And we notice that the maximum of impact toughness will happen if A equal to -1, which means the low level, which means the horizontal print orientation, and the maximum value that we got is 7576. And also to make sure that the experiment was done without any bias, we need to have a look on the residuals, and we notice it here that the residuals looks perfect. They are belong to normally independent distribution, and we don't have here any pattern. The same procedure we did in the impact toughness, we also implemented on the tensile strength, and we noted again that only the print orientation is the only factor that affects the tensile strength. And using Minitab, we also got equation to predict the tensile strength given the print orientation, and the maximum value of the tensile strength happens when we print the parts in the horizontal print orientation, which is 56.39. And again, we also check the residual to make sure that the experiment itself was done without any bias. So this is the main experiment. Usually after you are done with the main experiments, we need to verify the results that we got from this main experiment. So as I said, we already make a half fractional experiment, which means we did only used only 16 factors, 16 runs out of the 32. So usually after we make the main experiment, we make some verification experiment using the unseen or unused 16 experiments that we didn't include in the main experiment. So here we used only 4 of them to check if the results really works with unseen factors. So here we notice that for the recorded values, the values that we got for the one of them is 25. We check that if this value is within the low and high limit. Where we got the low and the high limit of the tensile strength, we will have some prediction from the equations that we got from Minitab for tensile strength, and we also got the standard deviation. If we subtract and add this value, we got the low limit and the high limit. If our experiment works well, the recorded value should be within the low and high limit. If it is less than the low limit or it is higher than the high limit, this means we have some problem in our experiment and the result doesn't work well. As you see here, we have the values for the vertical and horizontal print orientation, basically between the low and high level. And also we have the impact toughness for the vertical and horizontal print orientation, also between the low and high level, which confirms the results that we got. Why we only care about the part orientation? Because basically in the experiment, this is the only significant factor that we got. So that's all. Let's conclude what we did. Basically, we investigate the mechanical parts of the three-parted printed by Prusa by using two types of tests, which is tensile strength and impact toughness. He basically did fractional factorial experiments with five factors, and out of these five factors, we noticed that only one factor really affects the impact toughness and the tensile strength. And we also implemented some verification experiment to make sure that the result that we got from the main experiments really work on the untested conditions. Thank you for your attention and any question. Anyone have a question?
Thank you, Dr. Amna, for your presence and presentation. Does anyone having any queries? I hope there are no queries. Once again, thank you, Doctor, for your presence and presentation.
Thank you.
Now let's move on to the last presentation. It's from Dr. Amara Chukwu Obi from University of Nigeria, Nigeria. Hello, Dr. Obi, are you ready with the presentation? Hello, Dr. Obi. Can you please unmute yourself?
Can I share my screen?
Okay, now I'm making you as a presenter. Kindly click on the screen button to share your screen, please. Yeah, your screen is shared. Please open your PowerPoint presentation.
Yeah, let me share my screen. So,
Hello, Dr. Obi. Hello, Dr. Obi. Hello, Dr. Obi. Are you ready? Hello, Dr. Obi. Hello, Dr. Obi. Can you please unmute yourself? Hello, Dr. Obi. Can you please unmute yourself? Hello, Dr. Obi. Just minimize that folder. Just minimize that screen. No, don't close the app. Just wait. Just minimize that. Please unmute. Select unmute. Hello, Dr. Obi, can you please unmute yourself? Hello, Dr. Obi, can you please unmute yourself?
Are you hearing me?
Yeah, you're audible. Can you please?
Yeah, yeah. Can
Okay,
you open
please
up?
follow.
Let me share the screen now. Let me share the screen. My system hanged.
Okay, okay. Please follow my instructions. Please be
Yeah.
unmute. Share your. I will give presentation access to share your screen. Please don't close the GoToMeetings app. Just switch your apps in your mobile phone. Don't close the GoToMeetings app while sharing. Okay.
Yeah.
Just you
Let
can
me share
switch
it
between
now.
the apps. Yes.
Yeah.
Just
Yeah.
switch between the apps. Okay. Now don't close the GoToMeetings app. Please go to your home and open your PPT
Okay.
presentation from your
Oh,
mobile phone.
okay. 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 I don't know.
No, no, don't close, please.
Okay. Um. I don't know. He's saying go. Is
Wait,
isn't
wait,
responding.
click on wait.
Okay. Okay.
Okay, please go to your home of your mobile phone.
Okay. 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 Let me go to my home of my.
Hello, Dr. Ambi, can you please share your presentation to the program manager, Christian, through WhatsApp? We'll display your presentation from our end. As Dr. Obi, your presentation has been received. We will be sharing your presentation from our end. Yes, yes, it is your presentation here. Please start your presentation.
Yeah. Okay. Okay. Thank you, ma. Thank you so much.
Okay, please indicate us with the next when you want to change the slide. So we'll be changing the slide.
Okay. So I can start now.
Yes, you can start.
Okay. Good afternoon, all. My name is Amarachuku Obi from the University of Nigeria, Nsukka, Department of Mechanical Engineering, Faculty of Engineering. I'm also a researcher at the African Center for Sustainable Power and Energy Development, ACSPED. So this project was a B engine project in my department, Department of Mechanical Engineering, with my student, Ubo Obumneme Chukwemeka. Next slide. Okay. So the topic of the presentation is a 3D printed support for the vertical axis wind turbine blade. So it is a wind turbine blade. That's the 3D material we use in supporting the blade. Next slide. So the aim of this work is to design a support system using a 3D printable material from our lab for a vertical axis wind turbine, a B engine project. Next slide. So as you can see, the abstract is about the construction of and the testing. We tested it, a three-dimensional 3D support for vertical axis wind turbine blade. So this is what I'm presenting now. The support for the blade has an almost a semicircle shape. It's curved. It's a semicircle shape with a 2 millimeter thickness of the wall. of the wall support on one half. That's one half is 2 millimeter thickness. There's one half of the semicircle, and the 2 millimeter thickness on the other half of the semicircle. Of course, when we go down, we'll see it. So the 3D printed support for the vertical axis wind turbine blade is hollow in nature. It's a hollow housing a 1 millimeter thick aluminum sheet for reinforcement. We use this aluminum sheet thickness 1 millimeter to reinforce the printed material. So though the printed support is almost a semicircle, the assumed radius, of course, the radius of the semicircle is about 274.63 millimeter. So the material we use in printing the wind turbine blade, in printing the support for the wind turbine blade is PETG. Of course, we know the full meaning of PETG. So the model of the 3D printer is original Prusa i3MK3S Plus. Of course, the material proved strong. It's the result compared with literature. Next slide. Next slide. Okay. So the 3D, of course, we all know what a 3D printing is. It's an additive manufacturing process. Of course, of 3 dimensions. It's a 3-dimensional object from digital file. So the creation of a 3D printed object is achieved using, of course, additive processes by adding up creation, adding up of layers. Of course, presently there is a new research on 3D, the one they call volumetric 3D printing, is in phase now. Is a new type of 3D printing now. Next slide. Next slide. Next slide. Next slide. Next slide. Okay. So the machine, of course, we will see down there is down this slides, you will see the machine. So the machine we use, we see down there. So this is the vertical axis wind turbine. That's the wind turbine, the way it looks like. So next slide. Next slide. Next slide. So this is the 3 model of, okay. So as you can see, this is the semicircle dimension of the 3D printed support for the vertical axis wind turbine. You can see the support. It's about of course we've seen the radius. The radius is about the radius there is in the, I think we saw the radius earlier. The radius earlier showed that it's about 274.63 millimeter. That's the radius of this support, this 3D printable support. Next slide. So you can see, of course, that's still the support, the thickness of the support as it is produced, or as it was produced from the Prusa machine in our lab at AC Sped there. So this is how the support looks like. Next slide. So this is the machine, the Prusa i3MK3S machine is there in our lab at AC Sped lab. The AC Sped African Center for the center. That's in our center for African Center for Sustainable Power and Energy Development, AC Sped. That's where it's stationed. That's where the machine is stationed, and we used it. there. Next slide. So, of course, you can see the printing of the supports on the machine. So, so you can see the other one when it finished printing it. So, as you can see, these are the machines. Then you can see, yeah, you can see the other one down there is when the machine finished printing the support. So next slide. Next slide. Next, so you can see the aluminum sheet that is inside the 3D material. So the aluminum sheet was reinforced with a 3D material. So aluminum sheet is used out the up one, the aluminum sheet down there is when aluminum sheet was reinforced with the material, the 3D material. That's the down one there is the blade setup. So this is how it looks like. Next slide. Yeah. That one is the support system for vertical axis wind turbine. That's how the support system looks like. Anyway, the support structure of the vertical axis wind turbine. Next slide. Yeah. So that was when the whole system was coupled together, and that was where we tested it. Anyway, we used the artificial wind to test it. So this is where we tested it, the venue where we tested the wind turbine, the B engine project wind turbine, vertical axis wind turbine. Next slide. Of course, when it was tested, it showed that the material, the 3D printable material for the support system is very good, and really, it really compared well with literature. Next slide. Thank you.
Thank you, Dr. Obi, for your presence and presentation. Does anyone having any queries?
Yeah, thank you. Thank you, ma'am.
I hope there are no queries. Once again, thank you, Doctor, for your presence and presentation.
Yeah, thank you.
So, thank you.
Yeah, thank you, ma'am.
So, by this, we have came to end of our day one virtual conference. I would like to thank all attendees and participants of today's virtual conference. Hope you have enjoyed it and request you to attend tomorrow's session too. Thank you. Have a nice day.